The Observable Universe Theory. The night sky seems quiet, but what it hides is a story so vast that it collapses any notion of importance we may cling to. The Observable Universe Theory is not just a scientific statement. It's a humbling confrontation with the limits of what we are capable of seeing, measuring, and understanding. The phrase itself contains a hidden warning. Observable does not mean all there is. It simply defines the edge of our vision, not the boundary of reality. Beyond what we can see may lie not just more stars or galaxies, but entire unknown laws, infinite possibilities, and dimensions of existence that our minds cannot yet begin to comprehend. When we say the observable universe, we refer to the cosmic bubble that surrounds Earth, stretching out roughly 46.5 billion light-years in every direction. It's a sphere centered around us not because we're special, but because that's as far as light has had time to reach us since the beginning of time. This sphere is not defined by walls or borders, but by light, tiny messengers that have been traveling across a vacuum for billions of years just to gently touch our telescopes. We are seeing galaxies not as they are now, but as they were when their light first began its journey toward us. Some of the starlight hitting your retina tonight began its voyage long before humans existed. You're not looking at a star. You're looking at a fossil of fire, suspended in space-time, whispering the story of an ancient moment. This means that our view of the universe is not just limited in space, it is limited in time. The farther we look, the further back in history we see. Our observational horizon, then, is a bubble of space-time that locks us in a kind of cosmic solipsism, where the present is always hiding behind ancient images. But it gets stranger. Because of the accelerating expansion of the universe, many of the galaxies whose light we now receive are moving away from us so rapidly that, eventually, they will slip beyond our ability to ever detect again. In time, we will be able to see less of the universe, not more. Our observable bubble is shrinking in informational terms, even as the physical universe itself keeps stretching outward. This isn't science fiction, it's cosmological math. The galaxies we see today may already be unreachable, separated by expanding space, faster than light can catch up. They exist. We saw them, but we can never touch them. Not even light, the fastest thing in the universe, will bridge that gulf. In this sense, the observable universe is a haunted house of light, filled with ghostly images from a reality that no longer exists. And that's only what we can observe. The real universe, the totality of existence, could be infinitely larger than what we are allowed to see. There's nothing in the laws of physics that says the universe has to end at our observational edge. In fact, everything we know suggests the opposite. Just as standing on a beach doesn't let you see the entire ocean, staring into space doesn't mean we've found the edge of the cosmos. The observable universe is just the tip of an iceberg made of starlight and silence. Beyond it might lie more galaxies, more clusters, more empty voids. Or maybe copies of us, or universes with different physical laws entirely. And we have no way of knowing, because information from those regions hasn't had time to reach us. This is where the observable universe theory starts to feel more philosophical than astronomical. What does it mean to live inside a cosmic fishbowl, surrounded by walls of time and speed limits? What does it say about human significance when we realize that we might only be seeing a droplet in a cosmic storm? Astronomers estimate that there are roughly 2 trillion galaxies in the observable universe, each with hundreds of billions of stars. Multiply that by the number of possible planets, and you're dealing with a number so huge that it dissolves meaning. And yet, all of that, every galaxy we have ever mapped, every supernova ever studied, every light curve ever calculated, exists only within our observable patch. The true size of the universe could dwarf even that unimaginable scale into microscopic triviality. And still we observe. Because in our desire to look beyond the veil, there's something deeply human. The observable universe is not just a physical limit, It's a metaphor for our intellectual and emotional reach. It reminds us that there is always more to learn, more to see, more to imagine. It tells us that no matter how powerful our tools or clever our theories, we are still children tracing fireflies on the ceiling of an unfathomable night. It humbles us. And maybe that's the most important thing the observable universe offers, not data or images, but humility. The kind that silences pride. The kind that makes you whisper instead of shout. Because you realize that this planet, with all its drama, borders, wars, and worries, is just a dust mote suspended in an ocean of dark. This theory also changes how we think about the future. Eventually, as the universe keeps expanding, civilizations in the far future may see only darkness when they look up. The stars will have fled beyond their reach. To them, it might appear that they are alone, in an empty, static universe. The cosmic history we are privileged to witness today, of galaxies spinning and colliding, will become a myth to them, unknowable and unprovable. The observable universe is not permanent. It is a temporary gift, a window in time, and one day, that window will close. In a strange way, then, this theory becomes a kind of time machine. Not just in the literal sense, since we're looking back in time whenever we look far, but in the emotional sense. It transports us to a new awareness, one where our problems shrink and our wonder expands. The observable universe theory makes you feel small, but not in a way that diminishes you. It makes you small, like a child standing before the ocean, feeling the salt wind and waves crash, and knowing, deep in your bones, that the world is bigger than you will ever understand. And somehow, that's okay, because maybe being small is not a weakness. Maybe it's the beginning of awe. The multiverse theory. Imagine everything you know, this planet, this universe, this version of you, might not be all there is. The multiverse theory is a radical expansion of reality that proposes a mind-bending idea, that our universe is just one among countless others. Each of these universes could have different laws of physics, different histories, different versions of Earth, or no Earth at all. Some may be eerily similar, while others are unrecognizably alien. The multiverse isn't just a cosmic fantasy. It's a serious scientific hypothesis, born from deep within our understanding of physics, cosmology, and quantum mechanics. And if it's true, it means we are far smaller than we ever imagined, not just physically, but existentially. At the heart of the multiverse theory is a realization that the universe we observe might not be the only one. In fact, there's no compelling reason within physics that this universe must be unique. Our universe came into being during the Big Bang, a mysterious and explosive birth of space, time, and energy. But what if the Big Bang wasn't a singular event, but one of many? Some cosmologists suggest that what we think of as the universe is actually just a bubble in a much larger cosmic foam. Every bubble is its own universe, with its own beginning, its own physical constants, its own fate. This is known as the bubble universe theory, a version of the multiverse that emerges naturally from inflationary cosmology. Inflation theory tells us that in the very first slivers of a second after the Big Bang, the universe expanded at a speed far faster than light. This rapid expansion smoothed out space, created matter, and gave rise to the structure of galaxies. But according to some versions of the theory, inflation never stopped entirely. In certain regions it kept going, and still is. These ever-expanding regions continually birth new universes, each sealed off from the others like isolated soap bubbles. We live in one of these bubbles, but the multiverse stretches on, possibly forever, beyond the reach of our observation or imagination. Then there's quantum mechanics, the branch of physics that governs the very small. In quantum theory, particles don't have definite states until they're observed. Instead, they exist in a cloud of probabilities, superpositions of many possible outcomes. One interpretation of this strangeness is the many-worlds interpretation, which suggests that every possible outcome of a quantum event actually occurs, each in its own separate branch of the universe. If that's true, then every decision you make splits reality. In one universe, you turned left. In another, you turned right. In one, you took the job. In another, you never applied. There are universes where you made different choices, spoke different words, lived different lives. And all of them are as real as this one. This isn't just science fiction. It's a logical extension of mathematical frameworks already used in physics. The equations work. The theory holds. But whether we can ever test it, that's another matter. Some critics argue that if we can't observe these other universes, the theory falls outside the realm of science, but others point out that the same could once be said of atoms, germs, and black holes, ideas that were invisible until technology caught up. If the multiverse is real, we may eventually find indirect evidence, subtle patterns in the cosmic microwave background, or quantum anomalies that suggest branching paths of reality. Until then, it remains one of the most profound and unsettling possibilities we've ever considered. The implications of the multiverse are staggering. For one, it changes how we think about identity. If there are infinite versions of you, some nearly identical, others radically different, then what does it mean to be you? Is identity fixed, or is it simply the particular thread your consciousness happens to be following in a much larger web of possibilities? In one universe, you're reading this in a different language. In another, you never existed at all. Your joys, regrets, achievements, and failures, every one of them might be mirrored, inverted, or erased elsewhere. You are just one note in an eternal chord, a single vibration in a cosmic symphony. But the multiverse doesn't just challenge our personal sense of self, it also reshapes how we think about fate and free will. If every possible outcome happens somewhere, then nothing is truly impossible. There are universes where humanity never evolved, and others where it became a galactic civilization. There are realities where peace reigns, and others consumed by endless war. The future, in this view, is not a fixed line but a branching tree, endlessly forking into every conceivable version of what could be. Your choices matter in this universe, but in others, other choices were made. That doesn't cheapen your decisions. If anything, it makes this particular timeline all the more precious. Among infinite possibilities, this is the one you are living. Some versions of the multiverse go even deeper. In string theory, our universe might be a three-dimensional brain floating in a higher dimensional space. Other brains, other universes, could be stacked like pages in a book, each unaware of the others until they collide or interact. These collisions in some models might even spark new Big Bangs, birthing new universes in a never-ending cycle of creation and destruction. If this is true, then reality is not a static structure. It's a dynamic, evolving ocean of universes, bubbling with birth, collapse, and rebirth. The multiverse also offers an explanation for one of the biggest puzzles in physics, why our universe seems so perfectly fine-tuned for life. The physical constants, gravity, electromagnetism, the strong and weak nuclear forces, are balanced in such a precise way that if they were even slightly different, life as we know it wouldn't exist. Some see this as evidence of design, but the multiverse offers another answer. If there are infinite universes, each with different constants, then we just happen to live in one where the numbers align for life to emerge. It's not that the universe is tailored for us, it's that we exist in a universe where we can exist. Still, not everyone is comforted by the multiverse. For some, it's overwhelming, a dilution of meaning. If everything that can happen does happen somewhere, what's the point of anything? But this reaction misses something subtle. The multiverse doesn't make your life less meaningful, it makes it more miraculous. Out of infinite realities, you are here. Your consciousness has landed on this timeline. This is the version of the world that contains your experiences, your story, your thoughts. That uniqueness doesn't vanish just because other versions exist. In fact, it highlights the mystery of why you find yourself in this one. And there's still something beautiful in the unknown. The multiverse is not an escape from wonder. It is an expansion of it. It invites us to imagine not just what is, but what could be, what might exist beyond our senses, our tools, our comprehension. It makes the universe feel larger, yes, but also more connected, more alive, more filled with potential than we ever dared dream. We may never visit those other universes, we may never even confirm they're real, but the act of imagining them stretches the boundaries of what we consider possible. In the end, the multiverse theory doesn't shrink us, it enlarges the context in which we live. It doesn't make us insignificant. It makes the existence of this universe, of you, of now, a profound stroke of cosmic chance. And if that doesn't leave you humbled in the face of reality, perhaps nothing will. Because the real miracle may not be that there are other universes, but that in this one, you're here, wondering what lies beyond. Cosmic inflation theory. In the beginning, the universe was not as we know it now. There were no stars, no galaxies, no atoms, and certainly no people to ponder its mysteries. There was only an explosion, not of fire or sound, but of space itself. The Big Bang is often imagined as a sudden burst from a single point into an empty void, but that's a misleading picture. The Big Bang wasn't an explosion in space, it was an expansion of space. And what happened in the first fraction of a second after this event, the tiniest sliver of time imaginable, would determine everything that followed. This is the heart of the cosmic inflation theory, a period of unimaginably rapid expansion that stretched the fabric of space faster than the speed of light, setting the stage for the entire cosmos. To understand inflation, we must first abandon some of our most intuitive ideas about motion and growth. In everyday life, things grow linearly. A balloon inflates over a few seconds. A plant stretches up over weeks. But inflation wasn't gradual, it was exponential. In a period shorter than a blink, far shorter than the blink of any eye, even the flap of a photon, space itself expanded by a factor so large it's almost incomprehensible. In a time frame on the order from 10 to the minus 36 seconds to 10 to the minus 32 seconds, the universe grew from subatomic size to something perhaps the size of a grapefruit or larger. And then it slowed. Like a sudden gust of wind that hurls open the windows of reality, inflation happened fast, then stopped, leaving behind the energy and raw material for everything that would ever exist. But why propose such a wild theory? The answer lies in puzzles, inconsistencies, questions that standard Big Bang cosmology couldn't quite answer. For instance, why is the universe so uniform? When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see nearly perfect uniformity in temperature across the sky. Yet these regions should never have been in contact with each other. They are too far apart, even for light to have traveled between them in the time since the Big Bang. This is called the horizon problem. Another riddle is the flatness problem. Why is the geometry of the universe so finely balanced, hovering on the razor's edge between open and closed? Without some fine-tuning or mechanism, this flatness seems unlikely. And then there's the magnetic monopole problem, predicted particles that should exist in abundance but have never been observed. Cosmic inflation solves all of these problems in one bold stroke. If, in its earliest moment, the universe expanded at superluminal speeds, then regions now far apart were once close together, close enough to share energy, information, and temperature. The horizon problem dissolves. The flatness of space also finds explanation. Rapid expansion smooths out the curvature of space like pulling taut a wrinkled sheet. Even the elusive magnetic monopoles are diluted, stretched so thin by inflation that they may exist, but in numbers far too sparse for us to detect. Inflation doesn't violate the cosmic speed limit. While nothing can move through space faster than light, space itself can expand at any speed. It's not a speed limit violation, it's a loophole baked into the geometry of space-time. The metric, the ruler by which space is measured, was changing. Galaxies weren't moving through the universe like cars on a highway, they were being pulled apart, as the road itself stretched beneath them. And during inflation, this stretching occurred so rapidly that it took regions of space-time from quantum scales to cosmic scales in an instant. But what caused inflation, and what caused it to stop? These are still open questions. In most models, inflation is driven by a hypothetical field known as the inflaton, a scalar field that filled all of space. Like a stretched rubber band yearning to snap, the inflaton field stored potential energy that pushed the universe outward. When the field decayed, when its energy was released into the fabric of reality, it reheated the universe, filling it with particles, radiation, and matter. This moment is called reheating, and it marks the transition from the end of inflation to the start of what we think of as the classical Big Bang evolution: cooling, particle formation, atom formation, stars, galaxies, and eventually, observers. Quantum fluctuations in the inflaton field played a critical role. Inflation didn't just stretch space, it magnified tiny quantum jitters into macroscopic features. Regions slightly denser than their surroundings, once microscopic, were blown up to cosmic proportions. These fluctuations would become the seeds of cosmic structure, the precursors to galaxies, clusters, and the cosmic web. The very arrangement of stars in the night sky can trace its ancestry back to random quantum tremors amplified by inflation. This is one of the most extraordinary implications of the theory. The large-scale structure of the universe is the fossil imprint of quantum noise. We have evidence. The cosmic microwave background, mapped in exquisite detail by satellites like COBE, WMAP, and Planck, reveals a pattern of tiny temperature differences just as predicted by inflation. These patterns match the statistical fingerprints expected from quantum fluctuations stretched during inflation. The uniformity, the flatness, the correlations, all line up with what inflation says should have happened. While we cannot directly observe the inflationary moment itself, we see its fingerprints everywhere, encoded in the light of the ancient universe. Yet, like all great theories, inflation is not without its mysteries and controversies. For one, we don't yet know the nature of the inflaton field. It's a placeholder in our models, a mathematically necessary entity whose physical identity remains elusive. Some physicists wonder if it's connected to fields we already know, like the Higgs field. Others propose entirely new physics. And then there's the possibility that inflation never really ends. In some models, inflation is eternal. While it stops in some regions, creating bubble universes like ours, it continues in others, endlessly spawning new universes in a fractal-like cosmic foam. This idea ties inflation directly to the multiverse theory, suggesting that our universe is just one bloom on an infinite tree. This view opens doors both thrilling and troubling. If inflation produces countless universes, each with its own version of physics, then perhaps the fundamental constants we observe, like the strength of gravity or the charge of the electron, are not deeply determined by underlying laws, but are environmental accidents. We live in a universe where those constants allow for life, simply because in most others they don't. This anthropic reasoning is contentious. Some physicists embrace it as a necessary consequence of cosmic evolution. Others reject it, seeing it as the death of predictive science. But whether we accept inflation as the doorway to the multiverse or not, it has already transformed our understanding of beginnings. It shifts the narrative of creation from a singular moment to a dynamic unfolding. The Big Bang is no longer the beginning, but a phase change, a transition triggered by inflation's end. The deeper beginning, the moment inflation began, remains hidden behind a veil of speculation, quantum gravity, and unknown physics. Some theorists suggest that time itself may have emerged from a deeper, timeless state. Others look to string theory or loop quantum gravity to peer into the pre-inflationary past. But for now, we are left with mystery. And maybe that's the most honest outcome. Inflation explains so much, yet leaves us humbled before what we still don't know. It's a reminder that each layer of discovery reveals another veil, another horizon, another question, and yet how profound that we can even ask these questions, that beings made of star stuff living on a small blue planet can contemplate the first trillionths of a second of existence. The cosmic inflation theory stretches not just space, but our minds. It challenges our notions of cause and effect, of distance and scale, of randomness and structure. It invites us to consider that the very laws of nature and the universe they govern emerged from something deeper, stranger, and more primal. It hints at a time before time, at energy fields rolling across a newborn cosmos, at a moment when the universe was pure potential waiting to unfold. If you step outside on a cold, clear night and look up at the stars, what you see is not just distant light. You're seeing the aftermath of a great expansion. You're seeing a universe that once fit inside something smaller than a proton, now spread out over billions of light years. And all of it, every galaxy, every particle, every breath, is the echo of a moment that lasted less than a heartbeat but set eternity in motion. So when you think about your place in the cosmos, remember this: the universe is not old in the way mountains are old, worn slowly by wind and water. It is ancient in the way a thought is ancient, fast, fleeting, and filled with consequence. And perhaps, in that first impossible moment, when space itself leapt outward at a speed beyond light, the seeds were planted not just for stars and atoms, but for questions, dreams, and the longing to understand. Dark matter and dark energy. Most of the universe is missing, not in the sense that it's gone, but in the sense that we never truly had it. What we see when we look into the cosmos, stars, galaxies, nebulae, planets, is only the tip of the iceberg. It's the visible frosting on a vast, invisible cake of reality. For centuries, humanity believed that what we could see was what existed. But as telescopes became more powerful and physics more precise, a quiet and unsettling truth emerged. Nearly everything is made of something we cannot see, cannot touch, and cannot fully understand. It doesn't glow, it doesn't absorb light, it doesn't reflect it. And yet, it shapes galaxies, bends space, drives expansion, and dominates the mass energy content of the entire cosmos. This is the haunting mystery of dark matter and dark energy, the two unseen titans that make up 95% of everything that is. Let that number sink in. Everything we've ever observed, every star, every planet, every cloud of gas, every grain of dust, every photon ever detected, accounts for less than 5% of the total universe. The rest lies in shadow. And we are just beginning to realize how little we understand the stage on which our cosmic story unfolds. Dark matter and dark energy are not just mysterious, they are reminders of how limited our senses are, how much of reality remains veiled behind forces and structures we cannot directly observe. But their presence is undeniable. They make themselves known not by being seen, but by what they cause. Like wind through a forest or gravity bending light, they leave traces of their presence, writing their existence into the universe like a ghost author scripting a story we are just beginning to read. Let's begin with dark matter. The first hints of its presence came not from fancy modern instruments, but from the simple act of observation. In the 1930s, astronomer Fritz Zwicky was studying the motion of galaxies in a distant cluster known as the Coma Cluster. He noticed something strange. The galaxies were moving far too quickly. Given the visible mass of the cluster, the stars and gas, the galaxies should have flown apart. The gravitational glue required to hold them together just wasn't there. Unless, he reasoned, there was something else, something invisible, providing the extra gravity. He called it dunkel materie, or dark matter. At the time, the idea was radical, but decades later, it would be confirmed again and again, with new evidence piling up from every corner of the cosmos. One of the clearest signs of dark matter comes from the rotation curves of galaxies. When astronomers measure how fast stars orbit around the center of a galaxy, they find something unexpected. The stars far from the center move just as fast as those close to it. According to Newtonian physics, that shouldn't happen. The farther out you go, the slower the stars should move. Just like the outer planets in our solar system orbit the sun more slowly than the inner ones. But galaxies don't behave like that. Instead, they spin as if they are embedded in massive, invisible halos of extra mass. This mass has gravity, but no light. It doesn't emit radiation. It doesn't shine. It's there, silently shaping the movement of stars, and without it, galaxies would unravel like scattered sand. So what is it? What is dark matter made of? The truth is, we don't know. That's part of what makes it so haunting. It's not just ordinary matter that's dim or hidden. It's something fundamentally different. It doesn't interact with electromagnetic forces, meaning it doesn't reflect or absorb light. It passes through us, through Earth, through stars, almost like a ghost. The leading candidates are exotic particles called WIMPs, weakly interacting massive particles, or perhaps axions, or something even stranger that we haven't yet imagined. Enormous experiments deep underground, shielded from cosmic rays, are waiting for a whisper of dark matter to collide with a regular atom. But so far, the detectors remain mostly silent. We've mapped its gravitational effects with precision, but we have yet to catch it in the act of interaction. It's the most elusive mass in existence. And yet, without dark matter, the universe would be unrecognizable. Galaxies wouldn't form, stars wouldn't cluster. The cosmic web of structure, the vast lattice of filaments connecting galaxies across space, would not hold. In a very real sense, dark matter is the scaffolding of the cosmos. It is the invisible framework on which the visible universe hangs. You are here because dark matter shaped the formation of stars and galaxies billions of years ago. Without it, the ingredients of life would have never had a stage to emerge upon. But dark matter is only half of the mystery. The other half is even more disturbing. In the late 1990s, astronomers were measuring the rate at which the universe is expanding, using distant supernovae as cosmic mileposts. They expected to find that the expansion of the universe was slowing down. After all, gravity should be pulling everything back together, gradually, but what they discovered shocked the scientific world. The expansion wasn't slowing. It was accelerating. The universe wasn't drifting apart. It was being driven apart, as if by some unseen force. That force is what we now call dark energy, and it accounts for nearly 70% of the total energy content of the universe. Where dark matter pulls, dark energy pushes. It acts as a kind of anti-gravity, causing the fabric of space itself to expand at an ever-increasing rate. The more space there is, the more dark energy there seems to be, as if the very act of stretching space conjures more of the stuff. This runaway expansion means that distant galaxies are moving away from us faster and faster. Eventually, they will accelerate beyond the point where their light can ever reach us again. The universe is becoming darker, lonelier, and more isolated as time passes. In the far future, observers may look into the sky and see nothing. No other galaxies, no evidence of the Big Bang, no sign that there was ever anything else. Dark energy is erasing the cosmos in slow motion. What is dark energy? We don't know that either. Some suggest it's a property of space itself, a cosmological constant, as Einstein once proposed and later dismissed. Others think it might be a new field, like the inflaton that drove inflation. Or perhaps it's a sign that our understanding of gravity itself needs revision. Whatever it is, dark energy is not only mysterious, it's destiny-shaping. It determines the ultimate fate of the universe. If it continues growing unchecked, it could lead to a scenario known as the Big Rip, where galaxies, stars, planets, and eventually even atoms are torn apart by ever-increasing expansion. Everything we know could end in silence and separation. And yet, we owe our existence to the balance between dark matter and dark energy. Without dark matter, galaxies wouldn't form. Without dark energy, the universe might have recollapsed before stars could light up. Life arises in the narrow space between collapse and dispersal. in the pause between the pull of gravity and the push of the void. We live in that breath, that stillness, that equilibrium between two unknowns. Our entire story takes place in the thin slice of time where the forces are stable enough for structure, life, and consciousness to emerge. There's a quiet irony in all of this. For so long, we thought we were seeing the universe clearly, but we were only seeing its surface. The deeper we looked, the more we realized that the vast majority of what exists is hidden from us, not by distance, but by nature. Dark matter and dark energy do not hide behind walls or shadows. They are part of the very fabric of reality, present all around us, but fundamentally outside our direct perception. They are the negative space that gives shape to what we can see, the silence between the notes that makes the music whole. And perhaps that's the most humbling truth of all, that the universe is not only stranger than we imagine, but stranger than we can imagine. That our tools and senses, no matter how refined, may always fall short of the whole picture, and that the real substance of existence may always lie just beyond the reach of light. But we continue to search. We build telescopes that can see the birth of galaxies. We construct detectors that wait in silence for particles that rarely speak. We refine equations and maps and theories in an attempt to grasp what lies behind the veil, because even in the face of such darkness, the human spirit yearns for understanding. We are creatures of light, groping through shadow, and maybe that is what makes the mystery beautiful, that it asks us to reach, to wonder, to seek, even when the answers remain just out of reach. Dark matter and dark energy are not failures of science. They are signs that the universe is deeper than our current knowledge. They are invitations to keep going, to question, to imagine, to accept that what we see is not all that there is, and that maybe, in that mystery, there is a kind of grace. 95% of the universe is missing from our eyes, but in the act of seeking it, we see more clearly what it means to be alive. The simulation hypothesis. What if everything you've ever known, every sight, every sound, every emotion, wasn't real in the way you think it is? What if the stars in the sky, the ground beneath your feet, and even your thoughts were not products of a natural universe, but artifacts of code, part of a massive, hyper-advanced simulation running inside a computer system so complex that it defies understanding? This is the heart of the simulation hypothesis, a concept that seems at first like science fiction, but has gained serious attention among philosophers, physicists, and technologists. It's the idea that we may be living in a computer-generated reality, one indistinguishable from the real thing, constructed by entities with computational abilities far beyond our own. And if it's true, then everything we believe about existence, identity, and the nature of truth may be an illusion, running on a digital substrate we can never access directly. The simulation hypothesis begins not with fantasy, but with logic. In 2003, philosopher Nick Bostrom published a paper that laid out a trilemma, a choice among three possibilities. The first is that human civilization is unlikely to reach a level of technological maturity where it can run realistic simulations of conscious beings. The second is that even if such a level is reached, advanced civilizations would choose not to run such simulations. The third, and most unsettling, is that we are almost certainly living in one of those simulations. The reasoning is deceptively simple. If it is possible to simulate entire worlds, and civilizations do so often, then simulated realities would vastly outnumber original ones. Just as there are more replicas than originals, more copies than masters, most conscious beings would find themselves inside a simulation without ever knowing it. Statistically, it would be more likely to be a character in a simulation than to be the creator of one. But what would it mean if our reality were simulated? Would we be able to tell? Could the illusion be so perfect that it deceives all of our senses, all of our instruments, even our logic? The simulation hypothesis suggests that we wouldn't necessarily see any difference. After all, A sufficiently advanced simulator could program not only the behavior of matter, but also the perception of that behavior. If you think you see a tree, it's because your simulated brain is receiving simulated photons that follow simulated physics. If the rules of the game are internally consistent and your consciousness is part of the program, then your experience would feel every bit as real as it does now. Some believe there may be clues, glitches in the matrix, so to speak. Quantum mechanics, for instance, reveals a world that behaves probabilistically, not deterministically. Particles don't have fixed positions or velocities until they are observed. Some theorists wonder whether this is evidence of computational efficiency, that the universe only renders details when they're observed, like a video game engine saving memory by only displaying what's in the player's field of view. The speed of light might represent a processing limit. The Planck length, the smallest possible unit of space, could reflect the pixel resolution of reality. Cosmic rays, which should arrive at Earth in smooth, random distributions, sometimes display unexpected patterns, as if traveling across a lattice. Even the apparent fine-tuning of the physical constants that allow life to exist might be explained by simulation. Perhaps only simulations with those values are allowed to run, or perhaps we are a deliberately constructed experiment within a range of test conditions. But then comes the question, who would do this, and why? If our world is a simulation, then somewhere outside this bubble of reality there exists a higher reality. The entities that created our simulation may be vastly more intelligent and powerful than anything we can comprehend. To them, we might be no more than data, or we might be the center of a grand scientific project. Perhaps they are running ancestor simulations, virtual models of their own evolutionary past to understand their history. Or perhaps they are simulating universes as art, entertainment, or philosophy. We could be a game, a story, a study. Or we could be accidental, a byproduct of some higher-level computation that just happened to spawn conscious agents like us. And if that is the case, the simulation might not even be optimized for us or care about us. We could be inside a universe where suffering and joy are side effects of algorithms, not elements of design. This possibility redefines the idea of God. The simulators, if they exist, are not gods in the traditional sense, but they are God-like in power. They would have created our cosmos, chosen its rules, initiated its birth. They could pause time, alter reality, delete people, or reset the entire world. Miracles and anomalies might not be supernatural, they could be patches or interventions. Prophets and visions could be subroutines, and yet, unlike traditional gods, these creators may not be moral authorities. They may not watch us, judge us, or offer salvation. They may be indifferent or even unaware of our existence, like programmers who forget what their background processes are doing. Still, the simulation hypothesis doesn't require a belief in conscious creators. The simulation could be the result of a fully automated system. Imagine a future in which artificial intelligences build simulations not by desire but by necessity, replicating models of reality to solve problems, make predictions, or generate data. Our universe might be one instance in a recursive loop of simulations within simulations, with no clear origin, no first reality. And if consciousness can emerge from code, as many neuroscientists believe, then it could arise spontaneously in any system with sufficient complexity. You, then, might not have been created deliberately. You might have emerged like a pattern in chaos, an echo of cognition in a sea of data. But would that change your life? If tomorrow you found definitive proof that we are living in a simulation, what would it mean for your relationships, your dreams, your identity? Would it make your experiences less meaningful or more? Some argue that a simulated life is still a life. If your love is felt, if your sorrow is real, then it doesn't matter whether the atoms are real or virtual. Reality is defined not by what it's made of, but by how it is lived. Others believe that discovering we are simulated would strip the world of value, reducing human existence to the level of software, subject to deletion, manipulation, or irrelevance. But perhaps the truth lies somewhere in between. Perhaps knowing we might be simulated can inspire awe, not disillusionment. After all, if our creators designed us to explore, to question, to seek meaning, then understanding that we are part of a grand artificial universe would be the ultimate fulfillment of that design. The simulation hypothesis also invites deep ethical and philosophical questions. If we can create simulated beings who are conscious and capable of suffering, do we have moral responsibility for them? If we run millions of simulations to solve problems, are we condemning countless minds to brief, painful existences? And what does that mean for us if we too are the product of such a choice? Should we be angry at our creators, grateful, or simply curious? It also makes us reconsider the nature of death. If you are data, death may be deletion, or it may be a reboot, a transfer, a continuation in another form. Maybe nothing is lost, only rewritten. Maybe our memories are backed up in a server beyond comprehension. And yet, despite its elegance, the simulation hypothesis remains unprovable, or nearly so. Any simulation advanced enough to simulate reality would likely be advanced enough to hide itself. We could live our entire lives in this world without ever seeing its source code. Every test, every probe could be anticipated and accounted for. The simulation could be perfect, or close enough that its seams are never revealed, but that doesn't make the idea worthless. In fact, some scientists argue that it should be treated like any other hypothesis, examined, tested, and refined. They search for anomalies, mathematical structures, or physical boundaries that might suggest artificiality. They look for the edge of the program, the limits of precision, the ghost in the machine. Ultimately, the simulation hypothesis is not just a question about computers or technology. It's a question about reality itself. What is real? What does it mean for something to exist? Are we bodies in a world or minds in a model? These questions have been asked for millennia by mystics, monks, and philosophers. Plato's cave, Descartes' demon, the Buddhist concept of illusion, all echo the same uncertainty, that the world we see may not be the world that is. The simulation hypothesis is just the latest and most technologically resonant version of that timeless doubt. And maybe that's its real power, not to provide answers, but to sharpen our awareness, to remind us that our perceptions are limited, our knowledge incomplete, that behind the veil of familiarity, reality may be stranger than we imagine. Whether we are biological or digital, evolved or designed, we are still seekers of truth, still dreamers within a system we do not fully understand. And maybe, just maybe, that is what makes us real. Not our particles or pixels, but our wonder. Not our origin, but our curiosity. Not the certainty of the world, but the fact that we question it. So the next time you look at the stars, consider this. They may be real suns lighting real galaxies across real distances, or they may be glowing pixels in a cosmic engine rendering night for your eyes alone, but either way, they are beautiful. And the feeling you have when you see them, that surge of awe, that stillness in your soul, that is real. Because whatever this is, it is the only world you've ever known, and for now that is enough, the heat death of the universe. In the vast stillness of space, stars burn with intensity and life. They pulse and glow, forge elements in their cores and illuminate the galaxies. But their light is not eternal. Every star that shines is using up its fuel. Every galaxy that twirls is slowly unwinding. Every action in the universe moves toward equilibrium, toward balance, toward stillness. And according to the most accepted projections of cosmology, this journey ends not in fire or collision, but in cold, quiet darkness. This is the heat death of the universe, a haunting and inevitable scenario in which time does not end with a bang, but with a fade. It is the final chapter in a book that spans eons, a chapter written in silence, stillness, and absolute thermodynamic equilibrium. To understand the heat death, we must first understand entropy. Entropy is a measure of disorder, of randomness, of how evenly energy is spread out in a system. In any closed system, entropy tends to increase. Energy moves from concentrated forms to diffuse forms. A hot object cools, a spinning object slows, a structured system decays into chaos. This is the second law of thermodynamics. The universe, it turns out, is a closed system. It began in a state of low entropy, highly ordered and filled with usable energy. But as it expands, entropy increases. Energy becomes more spread out, more uniform. Stars burn through their fuel, releasing heat and radiation that slowly fills the vastness of space. And once this energy is used, once it spreads too thin, it can no longer do work. The heat death is not the fiery end that science fiction often imagines. It is the death of change, the cessation of useful energy. It is a universe that has reached maximum entropy, where everything is evenly distributed, where temperatures are uniform, and where no gradients exist to power movement, life, or thought. In this final state, all processes that require energy cease. No new stars form, no light pierces the void, no structure survives. The universe becomes a thin, cold mist of particles drifting through an endless, empty night. But this end will not come quickly. It will unfold over incomprehensible timescales. Stars will live out their lives over billions of years, fusing hydrogen into helium and eventually exhausting their fuel. The largest stars will go supernova, leaving behind black holes and neutron stars. Smaller stars will swell into red giants, then collapse into white dwarfs. These white dwarfs, still hot from their internal pressure, will slowly cool over trillions of years, becoming black dwarfs, cold, dead cinders in space. The universe, once filled with light and energy, will become darker as each star winks out, one by one. Galaxies will lose cohesion as their stars burn out. The night sky will become emptier, and over unthinkable epochs, even the remnants will erode. Protons may decay, a process not yet observed but predicted by some theories, reducing matter itself into subatomic haze. Black holes, the last gravitational behemoths in the universe, will begin to evaporate through Hawking radiation. This process takes time, more time than all the life of the universe combined, 10 to the 100th years or more. But eventually, even black holes will vanish. Nothing, not even gravity wells, will survive. And what remains then? A dilute sea of photons, neutrinos, and the occasional low-energy particle. A universe without contrast, without direction, without memory. There will be no events because events require change. There will be no observers because observation requires complexity, and complexity requires energy. The universe will not be dead in a dramatic sense, but functionally frozen in its final lowest energy state. It will persist in a state of eternal drift, without motion, without light, without time in any meaningful sense. Because when nothing changes, time loses its meaning. The idea of heat death is not new. It was first proposed in the 19th century by physicists like Lord Kelvin and Rudolf Clausius, who studied thermodynamics and recognized the implications of entropy on a cosmic scale. But back then, the universe was thought to be static. The Big Bang model had not yet emerged. It wasn't until the 20th century, with the discovery of cosmic expansion and the background radiation left over from the early universe, that heat death became the dominant cosmological forecast. The evidence is strong and the logic is simple. If the universe keeps expanding and energy keeps dispersing, then eventually everything will flatten out. This vision of the end is stark and unsettling. It offers no rebirth, no final climax, no escape. It is not an apocalypse, not a war of gods, not a celestial firestorm. It is the final breath of a cosmos that has used all its potential and settled into a whisper. For some, this notion is deeply depressing. It suggests a meaningless end to all things, a kind of cosmic nihilism, where even the stars are destined for silence. For others, it is a source of strange comfort. The universe is not cruel. It is indifferent. It simply follows its laws, and those laws lead to stillness. That stillness is not malevolent, it is serene. It is the quiet after the storm, the exhale after a long, creative breath. The heat death also challenges our idea of immortality. No civilization, no matter how advanced, can outrun entropy. Even if we harness stars, build Dyson spheres, and colonize galaxies, the energy will still run out. No machine can run without fuel forever. No memory can persist when its medium decays. Over infinite time, even the greatest accomplishments will be erased, not by malice, but by the slow undoing of energy itself. If we seek eternity, we must find it not in permanence, but in the present, in what we build and love and understand while the lights are still on. Still, some thinkers have imagined ways out. Perhaps the universe will one day reverse its expansion, a scenario known as the Big Crunch, but the evidence points against this. Dark energy, the mysterious force driving accelerated expansion, appears to be growing stronger. Perhaps we could create pocket universes, escaping into new realities before this one dies. But even that would require energy, and the window to act may close long before we're ready. Or perhaps, like digital simulations, the universe will be rebooted or copied, the end feeding into a new beginning. These ideas are speculative, fascinating, but unproven. For now, the heat death stands as the most likely future of everything, a slow, cold march into darkness, a curtain falling not with noise, but with silence so complete that nothing remains to witness it. And in that silence, we are reminded of the preciousness of now, the fact that we live in a golden age, a thermodynamic miracle where stars still shine, where energy still flows, where complexity still thrives. We live in a tiny, brilliant window between origin and oblivion, and everything we love is a product of that window. It also forces us to reflect on meaning. If the universe ends in darkness, does that make life meaningless, or does it make it more meaningful? If the story ends in silence, does that diminish the story, or does it elevate every chapter that came before? Every star that burned, every life that thought and felt and hoped, those moments are not undone by the ending. They are framed by it, defined by it. The light means more because we know it won't last. The warmth of life means more because the universe trends toward cold. Entropy does not erase significance, it highlights it. It tells us that structure is rare, that awareness is fleeting, that beauty is a temporary alignment of matter and energy, and that is precisely what makes it beautiful. We are not here forever, but we are here now, and that now is everything. The heat death of the universe may be the ultimate fate of all things, but it is not the only story the universe tells. It is the final act. But before that comes an epic tale of creation, evolution, struggle, and wonder. Stars rise and fall. Civilizations bloom and vanish. Life reaches out, questions the dark, builds meaning out of chaos. And that meaning is not erased by the end, it is rendered more poignant by it. So as we look to the future, not just of our species but of existence itself, we carry with us the knowledge that everything changes, that everything cools, that everything fades. But we also carry the light of understanding, the fire of curiosity, the brief but brilliant awareness that we are part of something vast, something temporary, something miraculous. The heat death may be the end of time, but it is also the reason that time matters. It gives urgency to our days, weight to our decisions, and gravity to our love. And in the face of that cold, empty end, perhaps the most defiant thing we can do is simple: to burn while we can, to think, to feel, to build, to remember. To be the light that once danced in a darkening universe. And when the last light goes out, to know that, for a time, we were here. Cosmic Horizon Theory. There is a limit to how far we can see. Not because our telescopes aren't powerful enough, and not because the light isn't bright enough, but because the universe itself is expanding so fast that some galaxies are moving away from us faster than the speed of light. This boundary, invisible and profound, is known as the cosmic horizon. It is the edge of our observable universe, not marked by walls or borders, but by time, by distance, and by the speed of the universe's own expansion. It defines what we can know, what we can ever witness, and what will forever remain beyond our reach. The cosmic horizon theory is not just a scientific fact, it's a haunting reminder of the limits built into the very fabric of space and time. When we look out into the night sky, we're not just looking across space, we're looking back in time. The farther away an object is, the longer its light takes to reach us. The moon's light is a little over a second old. The sun's is 8 minutes old. The light from the nearest galaxy is more than 2 million years old. When we gaze at distant galaxies, we are seeing them not as they are now, but as they were when their light began its journey. The farthest thing we can see is the cosmic microwave background, the remnant glow from the moment the universe became transparent, around 380,000 years after the Big Bang. That light has been traveling toward us for over 13 billion years. It is the wall of firelight that defines the deepest observable past. But beyond that wall there is more galaxies, more stars, more space. The universe did not end at that horizon. That's simply as far as light has had time to reach us. The universe is likely much larger, possibly infinite, and because space itself is expanding, some of that space is receding from us so quickly that its light, no matter how long it travels, will never reach us. These regions lie beyond our event horizon, a line not of distance, but of speed and time, beyond which communication is impossible even in principle. Every second, more galaxies cross this horizon. Every moment, more of the universe becomes permanently inaccessible. This is not because galaxies are flying through space faster than light, but because space itself is stretching. Imagine the universe as the surface of a balloon. As the balloon inflates, dots on its surface move away from each other. The dots aren't moving through the balloon, they are being carried apart by the expansion of the surface. In the same way, galaxies recede not because they are speeding through the universe, but because the universe is expanding between them. According to general relativity, there's no limit on how fast space can expand. And when distant regions expand faster than light can traverse them, they become unreachable. Their light can no longer outrun the expansion. This leads to a sobering implication. There are galaxies whose light has already been emitted, but will never reach us, not because it doesn't exist, but because the space between us is growing too fast. We will never see them. We will never know them. And as time moves forward, the cosmic horizon tightens. Galaxies we can see today will fade from view in the distant future. Eventually, the only galaxies visible from Earth will be those gravitationally bound to us, the local group, including Andromeda, the Milky Way, and a handful of smaller companions. Everything else will vanish beyond the horizon, becoming invisible, unknowable, gone not because they cease to exist, but because the universe carried them away faster than the universe could let their light catch up. This paints a strange future for astronomy. In 100 billion years, cosmic observers will look up and see only one galaxy. They will have no evidence of the Big Bang, no microwave background, no expanding universe. They will see darkness where once there was fire. They will think they are alone, not because they are, but because the universe hid its past behind the veil of acceleration. We live in a privileged era, the era of light, when the universe is old enough for complexity to emerge, yet young enough that the cosmos remains visible. We stand at the window between ignorance and fading memory, and that window is closing. The idea of a cosmic horizon is not merely poetic, it's mathematically precise. The distance to the cosmic horizon depends on the age of the universe and the rate at which it expands. In our current model, that expansion is accelerating, driven by a mysterious force we call dark energy. This dark energy pushes galaxies apart with increasing speed, making more and more of them unreachable. There is a cosmological event horizon, a limit beyond which no signal, no information, no light can ever reach us, no matter how long we wait. It's the ultimate barrier, not built of matter, but of motion and time. This has philosophical weight. We often think of the universe as something we can eventually know fully, given enough time and technology. But the cosmic horizon says otherwise. There are parts of existence we will never access, not because we aren't smart enough, but because the universe itself says no. There is no spaceship fast enough, no telescope large enough, no future long enough. Beyond the horizon lies a cosmic silence, places we will never touch, stories we will never read, light we will never see. Entire galaxies may rise and fall, live and die, and their entire existence will unfold without ever leaving a trace in our sky. And it's not just about the physical limits of observation. The horizon challenges the very idea of objectivity. If what we can know is limited by where we are in the universe, then knowledge becomes local. Our understanding of the cosmos is bounded by our horizon. Other observers in distant galaxies would have their own horizons, different skies, different accessible regions, different truths. There is no universal vantage point. There is no God's eye view. The universe is fragmented by expansion, its truths split across unreachable domains. What is real is not what exists in total, but what can be seen, measured, and understood within the shrinking bubble of the visible. Yet even in its constraint, the cosmic horizon reveals the power of thought. We can't see beyond it, but we can imagine beyond it. We can model it, simulate it, reason about it. We know that more galaxies lie beyond. We know their stories will go on, even as they vanish from our sky. And that knowledge is its own kind of sight, a vision not of photons, but of inference, of theory, of understanding. In this way, we still reach across the horizon, not with eyes, but with minds. The cosmic horizon also reframes how we see the present. Every galaxy we observe is a message from the past. Every photon we detect was emitted long ago, sometimes before Earth existed. We are not seeing the universe as it is, we are seeing it as it was. And for the most distant galaxies, that past will forever remain the only thing we can know. The present state of those galaxies, their stars, their planets, their fate, that lies beyond the cosmic event horizon. We can never see them now. Only echoes, only history, only the ancient light that began its journey before the universe pushed them beyond our grasp. And still, we watch, we search, we trace the edges of the knowable, measuring the red shifts of galaxies as they flee, plotting their motion like detectives at a cosmic crime scene. We use the clues left behind to reconstruct what we can. We learn not just what the universe contains, but how fast it is erasing itself from view, and in that awareness we are humbled. We are reminded that we are not masters of the cosmos, but momentary participants in its fleeting display. The universe does not revolve around us, it is leaving us. But that doesn't render our observations meaningless. In fact, it gives them weight. To look up and know what you see will not always be there. That is a privilege. To live in a time when the cosmic microwave background still sings, when the galaxies still gleam, when the past is still legible in the sky, that is a gift. The cosmic horizon tells us that the clock is ticking, not just on our lives, but on the visibility of the universe itself. One day, the great stage will go dark, and everything we do to understand it now will become the record of what once was. And so the horizon does not only limit, it inspires. It draws a circle around what we can know, but urges us to fill that circle with meaning, with knowledge, with wonder. It asks us to pay attention while the universe is still whispering, to listen to the messages in the light before the light is gone, to remember that even if we cannot reach the stars, we can still hear them sing, and even if the horizon hides parts of the cosmos, it cannot hide the beauty of the questions we ask. In the end, the cosmic horizon theory is not a tale of defeat. It's a reflection of the structure of reality. It teaches us that limits are real, but so is the courage to explore within them. It reminds us that not everything can be known, but that does not make the search less meaningful. And it whispers a truth both sad and sublime, that we are here, now, on the edge of visibility, in the era when the universe still shares its secrets. And that is a wonder beyond words? The Anthropic Principle. Why does the universe seem to be perfectly arranged to support life? Why do the laws of physics, the constants of nature, and the structure of reality all fall within the narrow ranges that allow stars to form, planets to stabilize, chemistry to bond, and eventually life to breathe, think, and question its place in the cosmos? This uncanny precision, this seemingly miraculous alignment of forces and numbers, has puzzled scientists and philosophers for decades. And at the center of that puzzle lies the Anthropic Principle, an idea both simple and profound, comforting and unsettling. It suggests that the universe appears fine-tuned for life, not because it was designed for us, but because we are here to observe it. In other words, perhaps we shouldn't be surprised the universe is compatible with life, because if it weren't, we wouldn't be here to ask the question. At first glance, the Anthropic Principle seems almost tautological, a circular truth hiding in plain sight. Of course the universe allows for life. We are here, aren't we? But underneath that apparent simplicity lies a deep philosophical and scientific inquiry. The physical constants of the universe, the strength of gravity, the charge of the electron, the rate of cosmic expansion, the masses of fundamental particles, are not arbitrary. If any of them were just slightly different, the universe as we know it would not exist. Stars wouldn't ignite, atoms wouldn't bind, planets wouldn't hold atmospheres. Life, at least as we understand it, would be impossible. So why do the numbers fall just so? Why this universe, and not one of the infinite others that seem far more probable and far more hostile? The Anthropic Principle doesn't necessarily answer the question. Instead, it reframes it. It suggests that we must account for the fact that any explanation of the universe must be consistent with the fact that observers exist. We can only observe universes where observers are possible. It's a filter, a selection effect, a cosmic version of survivorship bias. Imagine thousands of seeds scattered across barren soil. Only the few that fall into fertile ground will sprout. If a seed could become aware, it might marvel at how perfectly its environment supports life. But that's not because the soil was designed for it. It's because life could only emerge where conditions were right. The Anthropic Principle suggests we are like that seed, born in one of the rare pockets of cosmic soil where life could take root. There are different flavors of the Anthropic Principle. The weak Anthropic Principle simply states that the conditions we observe must allow for our existence. It's not a bold claim, but a reminder to avoid confusing cause with coincidence. It prevents us from being surprised that the universe supports life when we could not be here to ask the question otherwise. The strong Anthropic Principle goes further. It suggests that the universe must have properties that inevitably lead to the emergence of observers. That life is not just possible, but necessary in some way. This veers into more speculative territory, bordering on metaphysics, perhaps even purpose. It raises the question, does the universe need observers to complete itself? Some see the Anthropic Principle as a cop-out, a philosophical sleight of hand to avoid explaining the fine-tuning of the cosmos. They argue that it doesn't really answer the question of why the constants are what they are. It merely restates that they are compatible with us. But others defend it as a necessary framework for understanding why we perceive the universe the way we do. We cannot step outside ourselves. We cannot observe the cosmos from a position of non-existence. So, any theory about why the universe is the way it is must begin from the fact that consciousness has arisen within it. And perhaps the anthropic principle is most powerful when combined with the idea of the multiverse. If there are infinite universes, each with different physical laws and constants, then it is no longer surprising that one of them supports life. In a sea of randomness, islands of order will occasionally emerge. We live in one such island not because it is the only one, but because it is the one where life could evolve and ask questions. All other universes remain silent, not because they are empty, but because they are unobservable by minds that do not and cannot exist within them. In this context, fine-tuning is not evidence of design, but of selection. It's not that the universe was tailored for us, it's that only a universe like this could host beings like us. The probabilities are not meaningful outside of that framework. It's like asking why Earth has the perfect atmosphere for human lungs. The answer is not that the Earth was made for humans, but that humans evolved in response to Earth's condition. If Earth had a different atmosphere, we would not exist to wonder about it. But for some, the anthropic principle hints at something deeper. Perhaps it is not just a filter of observation, but a clue to the nature of reality itself. Some interpretations of quantum mechanics suggest that observation plays a fundamental role in determining the state of the system. In this view, the observer is not a passive viewer, but an active participant in the unfolding of reality. Could it be that the universe requires observers? That consciousness is not an accidental byproduct, but an essential part of the equation? If so, then the anthropic principle might be more than a selection effect. It might be a bridge between matter and mind. Others reject this as too mystical, too speculative. They prefer a universe that is indifferent, mechanical, blind. A universe that produced life by chance, not design. But even in that cold frame, the anthropic principle still holds. It says that the questions we ask are shaped by our survival, that the reality we measure is the one we are allowed to see, and in that truth lies a certain beauty. It reminds us of our contingency, our fragility, our miraculous emergence from a vast, uncaring void. It reminds us that we are not guaranteed, not necessary, not inevitable, and that makes our existence all the more precious. The anthropic principle also invites a subtle humility. It teaches that our perspective is not universal, that what seems fine-tuned to us may be the product of a deeper randomness, that what feels designed may be the artifact of chance, constrained by survival. It doesn't diminish our place in the cosmos, it contextualizes it. We are not the center, we are not the purpose, but we are here, and that is extraordinary. And perhaps in the quiet of this realization, we can find a different kind of meaning, not one imposed from above, but one constructed from within. The universe may not have been made for us, but we can make something of it. We can explore it, understand it, reflect upon it. We can take the raw material of chance and shape it into thought, into art, into love. We can be the eyes through which the universe sees itself, the voice through which it wonders, the heart through which it dreams. So when we marvel at the stars and whisper how strange it is that we are here at all, the anthropic principle gently nods. Of course it is strange. Of course it feels unlikely. But that feeling is itself part of the filter, part of the structure, part of the paradox. We are rare, not because we are chosen, but because most configurations of matter do not lead to awareness. We are improbable, but we are possible, and that possibility is enough. In the end, the anthropic principle may not give us answers, but it gives us perspective. It frames our questions within the context of our own existence. It reminds us that the universe is not only what is out there, but what is inside us, what we notice, what we can measure, what we can imagine. And in that awareness lies a quiet kind of truth, that to be alive in a universe that supports life is not a coincidence to fear, but a moment to cherish, not because it was made for us, but because, against all odds, we are here to see it. The Fermi Paradox. The stars are ancient. They burned long before Earth was born, and they will continue burning long after we are gone. Around those stars, countless planets revolve. some scorched, some frozen, and some, perhaps, just right. Given the vastness of space, the unthinkable number of stars, the unimaginable age of the cosmos, one would assume that life, especially intelligent life, should be abundant. It should have risen again and again, scattered across the galaxies like seeds on the wind. Civilizations should be common. Signals should be filling the void. We should not be alone. And yet we listen and we hear nothing. We look and we see no one. This is the haunting heart of the Fermi Paradox, the contradiction between the high probability of extraterrestrial life and the total absence of evidence for it. In a universe that should be teeming with voices, we are met with silence. The paradox is named after physicist Enrico Fermi, who, during a casual lunchtime conversation in 1950, famously asked, "Where is everybody?" The question cuts deeper than it seems. If intelligent life is common, it should have appeared millions, even billions of years before us. Given time, it should have spread. Even using slow travel, a civilization could, in theory, colonize an entire galaxy in a few million years, a blink in cosmic terms. And yet, we see no signs of such empires. No megastructures harvesting stars, no beacons announcing arrival, no shadows crossing the skies. Just us, a single species on a single rock, orbiting a very ordinary star. There are many possible explanations for the Fermi Paradox, but none are satisfying. Some suggest we are rare, that life itself is an extraordinary fluke, a cosmic accident that has occurred only once. Others think life may be common, but intelligence is rare. Perhaps microbes thrive on alien worlds, but evolution toward consciousness is staggeringly improbable. Still others argue that intelligence arises, but never lasts. Civilizations may destroy themselves before mastering space. Nuclear war, ecological collapse, artificial intelligence run amok. There are many ways for brilliance to extinguish itself. In this view, intelligence is like fire, bright, beautiful, and destined to burn out. Some explanations are more optimistic. Perhaps the galaxy is alive with life, but we are simply looking in the wrong way. Maybe civilizations communicate in modes we don't understand, using quantum entanglement or dark matter or concepts beyond our physics. Perhaps we are like ants trying to detect radio waves, surrounded by signals we lack the capacity to comprehend. Or perhaps they are silent by choice. A cosmic quarantine, some suggest, protects young species from contact until they are ready. Maybe Earth is inside a kind of zoo, or a lab experiment, or a spiritual initiation test. And perhaps the silence is not absence, but restraint. There's also the possibility that we are early, that life is just beginning to blossom in the cosmos, and we are among the first to awaken. In this case, the silence is not ominous, it is natural. The universe is vast and old, but stars like our sun are relatively young. Perhaps the conditions for life have only recently become widespread. If so, we may be pioneers, not the last to arrive, but the first to speak. The silence, then, is not a warning, but a stage awaiting its players. But for many, the silence is deeply unsettling. It suggests that something stops civilizations from spreading. This is known as the Great Filter, a hypothetical barrier in the evolutionary pathway from simple life to galactic colonization. The filter could lie behind us, in which case we are rare survivors of improbably difficult steps. Or it could lie ahead, a wall that no advanced civilization can pass. If the filter is in our past, then the emergence of intelligent life is incredibly rare. If the filter is ahead of us, then our doom may already be sealed. Either way, the silence is telling us something, we just don't yet know what. Some interpretations are even darker. Perhaps the universe is not silent, it's quiet, deliberately. Maybe civilizations go silent to avoid attention. Perhaps something predatory hunts intelligence across the stars. In such a universe, the first species to achieve interstellar travel eliminates all others to secure its dominance. If so, staying quiet may be the only path to survival. This idea turns the silence into a warning. Speak, and you may be heard. Be heard, and you may be destroyed. It is a chilling vision of a dark forest, where every life form is a potential threat, and silence is the only defense. Yet the paradox remains. The deeper we look into space, the older the light becomes. We are staring into the ancient past, across billions of light years. Any signal we detect now may have been sent before Earth had continents, and perhaps we are not alone, but merely asynchronous, separated not by space but by time. Civilizations may rise and fall like waves, never overlapping. The universe may be full of ghosts, empires long gone, voices long silenced, ruins spread across the stars that we will never see. The silence, in this sense, is not a void, but an echo. And still we listen. Radio telescopes sweep the skies, scanning for signals. Scientists search for atmospheric anomalies, for biosignatures in exoplanets, for patterns in cosmic noise. We send probes, messages, golden records, tiny bottles tossed into an ocean of space. We write equations, launch satellites, and whisper into the dark, because we want to know. The Fermi Paradox does not only raise questions about extraterrestrial life, it raises questions about ourselves. Why do we seek others? What does it say about the human spirit that, in the face of silence, we still speak? Perhaps it is because the question is not just scientific, but existential. To know whether we are alone is to know whether our story is singular or shared, whether life is a fluke or a thread woven into the fabric of the cosmos, whether we are the exception or the rule, and that knowledge would transform how we see ourselves. If we are alone, then life is rare and precious, a spark in the vast dark. If we are not, then we are part of something larger, a community of minds, echoing through the void. The Fermi Paradox does not need an answer to be powerful. It is a mirror held up to our assumptions. It reveals our loneliness, our curiosity, our fears. It shows how small we are and how vast our questions have become. And in its silence, it asks us to think deeply, not just about aliens, but about time, survival, intelligence, and meaning. Some say the silence means the universe is dead. Others say it means it is waiting. Some say it is proof of doom, others of potential. But perhaps the truth is not yet known because it is still unfolding. Perhaps we are the answer. Perhaps the silence ends with us. So we build telescopes and launch dreams and wait. We tell stories of what might be and wonder what watches from the dark. We ponder the stars not just as lights, but as questions. And the silence, so deep, so old, continues, not empty, not meaningless, but full of mystery, full of possibility. And in that quiet we remain, alone perhaps, but still listening. Boltzmann, Brain Theory. Close your eyes. Take a breath. Consider for a moment that everything around you, your memories, your body, your loved ones, the very room you're sitting in, is not real in the way you assume, not because it's a dream or a metaphor, but because it might be a statistical illusion. According to a strange and unsettling idea in physics called the Boltzmann brain theory, it is more likely that you are a single disembodied brain, spontaneously formed by a random fluctuation in a sea of chaos, hallucinating this entire experience, than that you are part of a vast, coherent, ordered universe. It is not a question of psychology or metaphysics, but of probability, entropy, and the logic of thermodynamics applied to the scale of eternity. The theory is named after the Austrian physicist Ludwig Boltzmann, one of the pioneers of statistical mechanics. Boltzmann sought to explain the arrow of time and the nature of entropy, the tendency of systems to evolve from order into disorder. He proposed that if the universe were infinite and eternal, then even highly ordered states could arise from randomness, given enough time. Imagine a universe that is mostly in thermal equilibrium. No structure, no stars, no life, just a uniform, empty void. Over time, purely by chance, particles might randomly clump together into brief pockets of lower entropy. Most of these fluctuations would be small, tiny eddies in a sea of chaos. But given infinite time, larger fluctuations would occasionally appear. Entire galaxies might arise momentarily from the void, only to dissolve again. And once, in a very, very long while, something stranger might occur. A single brain, complete with thoughts, memories, and sensations, might form, fully intact, from the chaos. This hypothetical entity, a Boltzmann brain, would emerge as a coherent arrangement of particles, just stable enough to experience a fleeting moment of consciousness before decaying back into entropy. It would have no history, no environment, no body, and yet, it might believe it has both. It might remember a childhood. It might feel love, pain, confusion, or joy. It might imagine a life filled with people, places, conversations, even the laws of physics themselves. All of it, memories, sensations, beliefs, would be illusions produced by the temporary structure of the brain itself. And here's the unsettling part. If the universe is infinite and eternal, and if entropy rules over time, then Boltzmann brains might be more common than real observers. Because it takes far less energy, far fewer particles, to create a single hallucinating brain than an entire universe filled with consistent, evolving structure. This creates a terrifying paradox. If such brains are more likely than real observers, then by the principle of typicality, by the logic that we are probably not special or unique, it's statistically more likely that you are one of them, that your memories are false, that your surroundings are a hallucination, that your entire existence is a momentary flicker of order in an endless void of disorder, and that you will vanish soon, leaving no trace, having never existed in any meaningful way. This is the philosophical heart of the Boltzmann brain problem. Not that such things could happen, but that if the universe works as some models suggest, they should happen more often than what we perceive as reality. Physicists and philosophers recoil from this conclusion, not because it's absurd, but because it might be logically correct. If our theories predict a universe dominated by hallucinating brains rather than structured worlds, then perhaps those theories are flawed, or worse, true, in a deeply uncomfortable way. The Boltzmann brain paradox acts as a kind of sanity test for cosmology. If your model of the universe leads to the conclusion that most observers are illusions, then perhaps your model needs revision. But if you reject the conclusion, you must explain why. Where did the logic go wrong? Was it in the assumption of an eternal universe? In the application of entropy? Or in the very idea of probability applied to conscious experience? One way to escape the paradox is to posit that the universe is not eternal, that it began with a low entropy Big Bang and will end before Boltzmann brains become statistically dominant. In this scenario, real observers like us are more likely than random brains, because the universe hasn't existed long enough for the hallucinating ones to outnumber us. Another solution is to question the application of probability to consciousness. Perhaps experience is not something that can be randomly assembled. Perhaps true minds require more than just a momentary arrangement of particles. Perhaps continuity, causality, and a real environment are essential to what we call awareness. And yet the idea lingers. It lingers because it forces us to confront a deep vulnerability in how we define reality. Most of us assume that what we perceive is real because it is coherent, sustained, and mutually reinforced by others. But what if coherence itself can be faked? What if your memories and sensations are not evidence of a past, but simulations generated by an improbable fluctuation? You believe you have a history, but that belief is just part of the illusion. You believe others exist, but those beliefs are encoded into the moment. You believe the laws of physics are stable, but in this hypothetical hallucination, stability is part of the dream. The Boltzmann brain problem is not science fiction. It is a serious question raised by the implications of entropy and probability theory applied to the cosmos, and it reveals something profound about how little we truly know. We take for granted that the universe is vast and consistent, that the stars have been burning for billions of years, that evolution, chemistry, and time have conspired to produce life and thought. But all of that is inferred. None of it is directly known. All we ever have is the present moment, the stream of conscious experience unfolding now. Everything else, memory, theory, science, and self, is constructed. And while that construction may be the result of a deep and meaningful cosmos, the Boltzmann brain theory asks, what if it's not? This line of thinking doesn't just challenge cosmology, it challenges metaphysics, epistemology, and the foundations of identity. It asks, what does it mean to be real? Is reality defined by external validation or by the internal texture of experience? If you feel love, does it matter whether the beloved exists outside of your mind? If you suffer, does it matter whether the pain is connected to a body or to a fleeting configuration of particles? These are not easy questions. They force us to peel back the layers of assumption that comfort us. Yet there is also something strangely liberating in the Boltzmann brain idea. If reality is uncertain, if experience itself is the only certainty, then perhaps we are freed from the tyranny of the external. Perhaps meaning is not grounded in the permanence of the world, but in the authenticity of the moment. If this life is a hallucination, but it feels real, is lived fully, and is filled with awe, does it lose its value, or does it gain it because it is the only one we will ever know? Most physicists view the Boltzmann brain theory as a reductio ad absurdum, a demonstration that certain assumptions lead to unacceptable conclusions. It motivates the search for cosmological models that avoid the problem. It pushes science to refine its understanding of entropy, of time, of the beginning and end of the universe. But for the rest of us, it serves a different role. It's a philosophical scalpel, cutting into the core of what we take for granted. It asks us to live in the tension between uncertainty and experience, to accept that the universe may be stranger than fiction, and that we may never know for sure. So what are we to do with this possibility? Are we to dismiss it as absurd, fear it as truth, or embrace it as a thought experiment that humbles the mind and sharpens the soul? Perhaps the best response is not despair, but wonder. Wonder at the fact that we can even pose such a question. Wonder at the possibility that our lives are meaningful, not because they are eternal, but because they are experienced. Wonder that, even if we are momentary configurations in a sea of chaos, we have thoughts, emotions, and dreams. And in that wonder, perhaps we find what matters most. Not whether this universe is real, but that we can ask if it is. Not whether our memories are accurate, but that they give shape to a self. Not whether the world exists beyond us, but that we exist, here and now, in a moment of consciousness that feels, questions, and dares to imagine. Whether we are the product of stars or of statistical flukes, we are here. And for now, that is enough. The Big Rip. The universe is expanding, not just the space between galaxies, but space itself. Every second, the cosmos grows wider, stretching the fabric of space-time a little more. For a long time, we believed this expansion was slowing down, tugged at by the gravity of all the matter it contains. But in 1998, astronomers made a startling discovery. The universe isn't slowing, it's speeding up. Something invisible, something we call dark energy, is driving this acceleration. We don't know what dark energy is. We only know what it does. It pushes galaxies apart faster and faster. And if this acceleration continues unchecked, or worse, if it increases, it may lead to the most dramatic and violent fate imaginable for the cosmos. This is the terrifying possibility known as the Big Rip. To understand the Big Rip, we must begin with what's already happening. As the universe expands, galaxies drift apart. The light from distant stars becomes redshifted, its wavelength stretched, its energy diluted. Over time, more and more of the cosmos slips beyond our observable horizon, pulled away faster than light can bridge the gap. Dark energy, it seems, is not just a force, it's a destiny. If its strength remains constant, the universe will coast into eternal coldness. But if dark energy intensifies over time, it will do more than separate galaxies. It will tear the universe apart, piece by piece, until nothing is left. This isn't poetic exaggeration, it's physics. The force of dark energy acts not like gravity, which pulls, but like a repulsive pressure that stretches space. If this pressure increases without limit, it will eventually overpower every force in nature. First, it will pull apart galaxy clusters, unraveling the structures that bind galaxies together. Then it will move inward, severing the gravitational bonds within galaxies themselves. The stars will scatter. Solar systems will come undone. Planetary orbits will disintegrate. The night sky will go dark, not because stars have died, but because they've been cast adrift into a sea expanding faster than their light can travel. But it won't stop there. As the Big Rip accelerates, it will begin to unmake things that were once thought indestructible. It will overcome the force that binds planets together. Earth itself will crack and shatter, not from an impact or explosion, but from the universe itself being stretched like taffy. Eventually, even atoms will fall victim. The electromagnetic force that holds electrons in orbit around nuclei will be overwhelmed. The atoms that make up your body, the molecules that form your brain, will be torn apart, and finally, in the last moments, just fractions of a second before the end, the nuclei themselves will disintegrate. Even the strong nuclear force, the most powerful known, will be defeated. The Big Rip is not a collapse, not a fireball, not a bang. It is a process of destruction by expansion. It is a universe that becomes too large, too fast, too wild for anything to hold together. It's a runaway effect, like a thread pulled too far until the fabric unravels. Unlike the heat death scenario, where the universe fades gently into darkness, the Big Rip is violent. It doesn't wait in silence, it screams apart in motion. Everything comes undone. Not metaphorically, not symbolically. The timing of this apocalyptic scenario depends on the nature of dark energy. If its strength increases rapidly, the Big Rip could occur sooner. If it increases slowly, the universe may endure for trillions of years before being torn apart. And if it remains constant or decreases, the Big Rip may never happen. We simply don't know yet, but some models suggest that if dark energy's pressure-to-density ratio, called W in cosmological equations, is less than -1, the universe is on a path to destruction. This value, called phantom energy, is not forbidden by the laws of physics. It's strange, but not impossible. And if phantom energy is real, it changes everything. It means the end will not be cold and quiet, it will be fast, hot, and catastrophic. The expansion will accelerate so rapidly that no force, no structure, no bond will survive. It means the clock is ticking, not just toward entropy, but toward explosion. Cosmologists have tried to calculate how this timeline might unfold. In the final billion years, galaxies will dissolve. In the final million, solar systems fall apart. In the last minutes, planets are shredded. In the final seconds, atoms are torn. The universe ends not with a whimper, but with a rip. There is something deeply unsettling about this vision. It violates our sense of permanence. It undermines the idea that some things are too small, too strong, or too sacred to break. It tells us that even the bonds that form matter, even the forces that shape existence, are vulnerable to the vastness of expansion. The Big Rip doesn't destroy the universe in a fire, it stretches it until nothing holds, until every particle is isolated, every force broken, every connection undone. It is the slowest explosion and the most thorough. Yet there is also something awe-inspiring in the scope of this idea, that the universe can tear itself apart, not from external damage, but from its own accelerated growth. That space itself, the silent stage of all things, can become hostile. It reminds us that we live in a dynamic cosmos, not fixed, not stable, but alive with motion and change. The laws we trust are not always gentle, the forces we rely on can turn, and the expansion we once thought passive can become violent. The Big Rip is a lesson in humility, a reminder that even the universe has limits, and that too much of anything, even space, can become destructive. Still, we should not panic. The Big Rip, if it comes, is far in the future, possibly tens of billions of years from now, long after Earth is gone, long after stars stop forming, long after memory fades. We will not see it. No one may. If life survives into those final eras, it will witness a universe fraying at the seams and perhaps find a way to leave, to escape, to shelter, or perhaps not. Perhaps there will be no one left, just the laws of physics, unfolding their final, irreversible chapter. But in the meantime, the possibility shapes how we think about the universe today. It adds urgency to our questions. It colors the silence of the night sky with tension. It tells us that time is not infinite, that space is not benign, that the end may not be soft. And it makes us look more closely at the data. Are we measuring dark energy accurately? Is it constant, as Einstein proposed? Or is it evolving, growing, waiting? Every telescope, every satellite, every calculation is part of that quest, to understand the fate that lies ahead. And perhaps, like many cosmological theories, the Big Rip will one day be revised, replaced, or disproven. Perhaps dark energy will stabilize. Perhaps quantum gravity will intervene. Perhaps the future holds surprises we cannot yet imagine. But until then, the Big Rip stands as a powerful possibility, a story the universe might be writing, word by word, in the shape of galaxies, the speed of light, and the distance between stars. In a way, the Big Rip is the ultimate lesson in impermanence. It tells us that nothing, not planets, not atoms, not even the laws of physics, is beyond change. And that in a universe driven by expansion, the very ground beneath our reality may someday be pulled away. But that knowledge does not need to bring despair. It can bring depth. It can sharpen our appreciation for now, for the stability we take for granted, for the bonds that hold, the orbits that last, the atoms that endure. Because right now, the universe still holds together. Stars still shine, Earth still turns, minds still wonder. And if the Big Rip reminds us that this won't last forever, it also reminds us to cherish what does, to seek, to build, to connect, to dream, while the cosmos is still whole, while the sky is still full of galaxies, while the laws of physics still protect us, for now, from the tearing apart of all things. So the next time you look at the stars, know this: you are seeing a universe in motion, a universe that may one day become too large for its own good, a universe whose end may not be an outside force, but its own acceleration. And in that knowledge feel not fear, but wonder. Because to understand the Big Rip is to glimpse the raw power of space itself, the fragility of all structure, and the mystery of a cosmos that still has secrets to unfold. Quantum entanglement. In the strange world of quantum physics, reality does not behave the way we expect. The rules that govern the everyday, solid matter, linear cause and effect, clear boundaries in space, begin to dissolve when we shrink down to the scale of atoms and particles. At this level, the universe becomes probabilistic, fluid, uncertain. One of the most mysterious and profound phenomena to emerge from this domain is quantum entanglement, a connection so strange, so counterintuitive that even Einstein called it spooky action at a distance. It describes a condition in which two particles, once linked, remain intertwined no matter how far apart they drift. Measure one and the other responds instantly, even if separated by galaxies. Entanglement challenges our deepest intuitions about space, time, and information, and it suggests that the universe is more interconnected, more unified, and perhaps more conscious than we dare to imagine. To understand entanglement, we must begin with the basics of quantum theory. Unlike classical objects, quantum particles do not have fixed positions or states until they are observed. They exist in superpositions, clouds of probabilities, hovering between possibilities. An electron is not here or there, but both. A photon is not vertical or horizontal, but some blend. When you measure it, the cloud collapses into a definite state. Before that, it exists in uncertainty. Now imagine two particles created in such a way that their properties are linked. Their spins, for example, are opposite. If one is measured to be up, the other will always be down. This is not surprising if they are close together, but what if you separate them by meters, by kilometers, by light years? Quantum mechanics predicts that they will remain entangled. Measure one, and the other's state is instantly known, no matter the distance. No delay, no signal sent, just a correlation that defies locality. It appears as though information has traveled faster than light, or as though the two particles are not truly separate at all. Einstein found this deeply troubling. In 1935, he and his colleagues Podolsky and Rosen published a paper designed to reveal what they believed was a flaw in quantum theory. They argued that either quantum mechanics was incomplete or it implied instantaneous action across space, which violated relativity. This thought experiment became known as the EPR paradox, and it sparked decades of debate. Einstein hoped that hidden variables, undiscovered pieces of information, would eventually restore a more sensible local reality. But in the 1960s, physicist John Bell devised a mathematical test that could distinguish between the predictions of quantum mechanics and those of any local hidden variable theory. And in the decades that followed, experiments consistently confirmed quantum predictions. Entangled particles do influence each other in ways that cannot be explained by local realism. Bell's theorem showed that if quantum mechanics is correct, then the universe is non-local. Space, in the way we intuitively understand it, is not a barrier. The fabric of reality is not stitched together by distances, but by something deeper, something holistic. Entanglement does not allow faster-than-light communication. The results are random. You can't control the outcome of a measurement. But the correlation is real, measurable, and persistent, and it raises profound questions. If one particle knows what happens to its partner across space, then what connects them? Is there an underlying field or dimension outside of space-time? Is our notion of separation, of here and there, an illusion, a useful fiction that breaks down at the quantum level? Some interpretations of quantum mechanics embrace this non-locality directly. The many worlds interpretation suggests that entanglement is a manifestation of branching realities. When a measurement occurs, the universe splits, and each outcome exists in its own world. The Bohmian interpretation, proposed by David Bohm, imagines an implicate order, a deeper, hidden layer of reality where everything is enfolded into everything else, and what appears separate is merely unfolded illusion. In this view, entanglement is not a trick or anomaly, it is a glimpse into the wholeness of the universe. And yet, entanglement is not just a philosophical puzzle, it is real, and it works. Quantum entanglement has been demonstrated with photons, electrons, atoms, even molecules. It underlies technologies like quantum computing, where entangled qubits perform calculations far beyond the power of classical bits. It powers quantum cryptography, enabling unbreakable codes based on the fundamental laws of nature, and it forms the basis of quantum teleportation, where information about a particle's state is transmitted to another, distant particle through entanglement alone. These are not fantasies. They are laboratory achievements, inching us toward a new kind of technology, a new kind of understanding. But the philosophical implications remain the most staggering. Entanglement suggests that the universe is not made of isolated parts, but of relationships, that particles are not tiny billiard balls bouncing independently, but events in a web of correlation. And if this is true on the smallest scales, what might it mean on larger ones? Are we entangled in some unfathomable way with distant parts of the cosmos, with other minds, with history, or future selves? Some thinkers have speculated that consciousness itself might be linked to entanglement, that awareness arises not from local brain chemistry alone, but from non-local connections. While this remains speculative, it reflects a growing sense that reality is not a machine, but a network, not a grid, but a tapestry. Entanglement invites us to see the universe not as empty space filled with objects, but as a vast field of connections, of resonances echoing across impossible distances. And it invites us to question the boundaries we take for granted. What does it mean to be here, if here can affect there instantly? What does it mean to be separate, if separation is only apparent? Entanglement blurs the lines between subject and object, between one particle and another, between one moment and the next. It suggests a cosmos where everything is in dialogue, even in silence, where everything influences everything else, even when it seems alone. Still, entanglement does not erase mystery. It deepens it. We understand the math. We confirm the results. But we do not know why the universe behaves this way. We do not know what mechanism lies beneath, and perhaps we never will. Perhaps entanglement is not a glitch, but a clue, a sign that our current framework is incomplete, and that something more profound lies beyond our equations. There is beauty in this mystery. There is wonder in a universe where particles whisper across galaxies, where distance is no obstacle to connection, where the rules bend and flow in ways our minds can barely grasp. Entanglement reminds us that the universe is not just strange, it is stranger than strange. It is deeper than logic. It is richer than certainty. And in that strangeness, we find meaning. Because if even the smallest parts of the cosmos are linked in such intimate ways, then maybe so are we. Maybe our thoughts, our choices, our lives ripple outward, entangled in ways we'll never see. Maybe love, memory, and meaning are not just products of neurons, but of a deeper order, an order that binds, that connects, that holds. So the next time you look up at the stars, consider that what seems distant may not be far, that what seems separate may not be alone, that somewhere across light years of space, a particle moves and another responds, not because of magic, but because of the universe's deepest truth, that nothing is truly apart. The Holographic Principle. What if everything you experience, the colors you see, the objects you touch, even your own body, were not truly three-dimensional, but instead the result of a projection? Not metaphorically, but literally. What if the entire universe as we know it, from the farthest galaxies to the deepest parts of your mind, was a hologram? This is not science fiction. This is the holographic principle, a mind-bending idea in theoretical physics that suggests our three-dimensional world might be an illusion, encoded on a distant two-dimensional surface. It sounds impossible, but it may be one of the most promising clues to understanding the nature of reality itself. The holographic principle finds its roots in black hole physics. In the 1970s, physicists like Stephen Hawking and Jacob Bekenstein began to explore the thermodynamics of black holes. They discovered something surprising. When an object falls into a black hole, its information doesn't seem to disappear, as one might expect. Instead, the entropy, or disorder, of the black hole increases in proportion not to its volume, but to the area of its surface. This defied expectations. Usually, the amount of information in a system scales with its volume, but black holes seem to operate differently. All the information about what fell in appeared to be encoded on the two-dimensional surface of the event horizon, the boundary that separates the black hole from the rest of the universe. This led to a radical idea. If information inside a black hole is stored on its surface, could the entire universe work the same way? Could everything we experience, space, time, matter, be the result of information stored not within our universe, but on its boundary? In the 1990s, physicist Leonard Susskind and others developed this idea further. They propose that just as a three-dimensional image can be encoded on a two-dimensional holographic plate, our universe might be a projection from a more fundamental two-dimensional reality. What we perceive as depth, volume, and motion may be emergent, a kind of cosmic illusion arising from a deeper layer of physics we cannot directly observe. In this view, the universe is a hologram, not in the way we use the term casually, not as a trick of light or an illusion in the everyday sense, but as a deep and literal truth about the structure of space and time. Just as a hologram can display a fully three-dimensional image from a flat surface, our universe may emerge from data encoded on a distant, lower dimensional boundary, perhaps at the edge of the observable universe, or perhaps in a dimension beyond our comprehension. The mathematics behind the holographic principle is both elegant and complex. One of its most compelling incarnations comes from string theory in the form of the AD/CFT correspondence developed by Juan Maldacena in 1997. This duality describes a relationship between a gravitational theory in a higher dimensional bulk, space, and a quantum field theory without gravity on its lower dimensional boundary. In simple terms, what happens inside a volume of space can be fully described by a theory that exists only on the surface enclosing that volume. The interior and the boundary are equivalent descriptions of the same reality. One has gravity, the other does not, but both contain the same information. They are mirrors of each other. This has profound implications. It suggests that gravity itself may be an emergent phenomenon, a result of deeper, non-gravitational processes happening on the boundary. It also offers a potential resolution to one of physics' greatest puzzles: how to reconcile quantum mechanics with general relativity. The holographic principle gives us a framework where quantum information is never lost, even in black holes, because it's always encoded on the surface. This preserves unitarity, the idea that information in quantum systems is conserved, and avoids the paradoxes that plagued earlier black hole models. But beyond the math, the principle challenges our deepest intuitions. We are used to thinking of the universe as a vast expanse, stretching in all directions, filled with stars and galaxies. We see depth, we experience motion, we believe in space. Yet the holographic principle suggests that these features may be illusions, effective descriptions of a more fundamental, information-based layer. What feels real to us may be like the moving image on a screen, compelling, detailed, and consistent, but ultimately the product of code running on a hidden surface. This doesn't mean the world is fake. It doesn't mean you are imaginary. It means that what you perceive as physical space is not fundamental. It emerges from something deeper. Just as temperature emerges from the movement of atoms, or solidity from the interaction of quantum fields, space itself may be a large-scale result of microscopic data encoded elsewhere. Reality in this view is not a thing, but a pattern, a vast interplay of information unfolding on the edge of existence. And yet, despite its strangeness, the holographic principle resonates with other areas of physics. It mirrors the way quantum entanglement connects distant particles, suggesting a deep unity beneath apparent separation. It echoes ideas from information theory, where everything that exists can be described by bits of data. It even aligns with ancient philosophical ideas that the world we see is a projection, a shadow of a deeper truth. Plato's cave, the Buddhist veil of Maya, the dreamlike quality of the world described in mystical traditions, all find strange harmony in the notion that what we perceive is not the full picture. Still, the principle raises new questions. If the universe is a hologram, then where is the projector? What generates the image? Is there a medium beyond the boundary? Is the boundary physical or purely mathematical? And what about consciousness? Does our awareness emerge from the hologram, or is it part of the code? These are not easy questions. The holographic principle does not answer them. It only opens the door. But in doing so, it shifts how we think. It invites us to see the universe not as a place, but as a process. Not as an object, but as a story, a narrative told by information, expressed through patterns, perceived as motion and form. It suggests that what we touch, what we see, what we fear and love are part of a grand equation, a cosmic script running on the edge of reality. And perhaps in this model there is a kind of grace. If we are patterns in a hologram, then we are connected, not just to each other, but to the whole. Each of us is a ripple in the same field, a voice in the same code. Our separation is apparent, not absolute. Our lives, our thoughts, our stories are woven into the same fabric that gives rise to stars and space. And that means we are not lost in a meaningless void. We are encoded in the logic of the universe itself. So the next time you reach out your hand or look up at the stars or feel your place in the world, consider this. Everything you see may be written on a distant wall, far beyond your sight. The light, the space, the distance, all may be an illusion, crafted by a deeper reality you cannot touch. And yet, that illusion is no less real. It is consistent, beautiful, and filled with meaning. Because even if the universe is a hologram, it is a hologram that thinks, that feels, that dreams. And in those dreams, we find ourselves. Planck Length. There is a limit to how small we can go, a scale so tiny, so unfathomably minute, that below it, space and time as we understand them no longer exist. This is the Planck length, often regarded as the smallest meaningful measurement in the universe. Not because we lack the tools to probe smaller distances, but because at that scale, the very fabric of reality unravels. Beneath the Planck length, the concepts of distance, duration, and even physical laws may lose their coherence. It is not just a boundary of technology, it is a boundary of nature, a veil beyond which our familiar picture of the universe collapses into mystery. The Planck length is named after the German physicist Max Planck, one of the pioneers of quantum theory. It is derived from a combination of three fundamental constants: the speed of light, the gravitational constant, and the reduced Planck constant. When you combine these in a particular way, you get a length, approximately 1.616 times 10 to the power of minus 35 meters. To understand just how small that is, imagine shrinking a meter by 35 orders of magnitude, each step reducing its size by a factor of 10. The Planck length is to a proton what a proton is to the entire solar system. It is smaller than small. It is the edge of everything. At this scale, space is no longer smooth and continuous. It becomes grainy, like pixels in a digital image. Quantum fluctuations dominate. Gravity, which usually behaves as a gentle curvature of space-time, becomes wild and turbulent. Waves of geometry twist and fluctuate. Time jitters. The familiar stage on which particles dance dissolves into foam. This chaotic realm is sometimes called quantum foam, a term coined by physicist John Wheeler. It is a sea of uncertainty, where even the geometry of space cannot be pinned down, and where the idea of here and there no longer applies. Why does this matter? Because the Planck length represents the limit where general relativity and quantum mechanics collide. Einstein's theory of gravity describes space and time as a smooth, continuous fabric. Quantum theory describes particles and forces as probabilistic and discrete. Both theories work beautifully in their own domains, but at the Planck scale, they clash. Gravity becomes quantum, and quantum mechanics becomes gravitational. To understand what happens at this scale, we need a theory of quantum gravity, something physics has yet to fully achieve. String theory, loop quantum gravity, and other speculative models attempt to describe this realm. But until we can observe or experiment at the Planck length, these remain theoretical visions, hints of a deeper truth, still out of reach. The existence of the Planck length forces us to question the very foundation of measurement. We are used to thinking of space as something that can be subdivided infinitely. But what if that's not true? What if there's a smallest unit, a smallest pixel of reality, beneath which space has no meaning? This is not an arbitrary limit. It is built into the equations of the universe. Just as a digital image cannot contain more detail than its resolution allows, the universe may not contain structure below the Planck scale. Trying to probe it would be like zooming in on a painting until all you see are individual brushstrokes. Beyond that, there is no more image. Attempts to measure distances smaller than the Planck length encounter paradoxes. To probe something that small, you would need particles with extremely high energy. But according to general relativity, concentrating that much energy into such a tiny space would create a black hole, preventing you from seeing anything inside. The very act of looking would destroy what you're trying to see. Nature, it seems, has a built-in censorship mechanism. It does not allow us to see below the Planck scale, not because we are limited, but because the universe itself has limits. This has profound implications. It suggests that space and time are not fundamental, but emergent, that they arise from deeper, more abstract principles, perhaps from information, entanglement, or something else entirely. In some theories, space-time is woven from networks of relationships between quantum states, like nodes on a graph or threads in a tapestry. The Planck length is the scale at which this underlying weave becomes visible. It is the smallest stitch in the cosmic fabric, the grain of the universe's texture. And if space is quantized, what about time? There is also a Planck time, the time it takes light to travel one Planck length. It is unimaginably short, about 5.39 x 10^44 seconds. Below this scale, time may not be continuous. It may occur in discrete jumps, like frames in a film. Our experience of flow, of duration, of causality may all be approximations built from countless flickers of existence. The river of time may not be smooth, but pixelated. For most of human history, space and time were seen as infinite, continuous, and absolute. The Planck length shatters that illusion. It tells us that the universe is finite in detail, that there is a bottom to the structure of existence, and it invites us to rethink what it means to exist. If you cannot define a location smaller than the Planck length, then the very concept of place becomes uncertain. If time cannot be divided beyond the Planck time, then causality itself becomes fuzzy. We are left not with firm ground, but with questions that blur into one another. And yet there is beauty in this boundary. The Planck length is not a wall, it is a threshold. Beyond it lies the unknown. But it also marks the point where all our best ideas converge. Gravity, quantum mechanics, and light. These three pillars of physics meet at the Planck scale. It is the forge where a deeper theory of reality must be born. It is the smallest possible arena of the cosmos, and perhaps also the seed of its deepest truths. Some thinkers imagine that the Planck length encodes the fundamental units of the universe, much like binary digits in a computer. In this view, reality is digital, not because it's a simulation, but because it is built from discrete elements. The constants of nature, light speed, Planck's constant, Newton's G, are the code. The universe is not analog, it is made of bits. This vision aligns with the holographic principle, with quantum information theory, with the idea that existence is not made of matter, but of information. Others speculate that the Planck length hides new dimensions. String theory suggests that the universe has more than 3 dimensions of space, but that these extra dimensions are curled up at the Planck scale, too small to detect. They may influence physics in subtle ways, or contain entire universes folded into microscopic corners of reality. If true, then the Planck length is not just a limit, it is a doorway, a boundary between the seen and the unseen, a whisper of hidden worlds. And even if we never observe it directly, the Planck length shapes everything. It is the foundation beneath our feet, the limit behind the laws, the invisible scaffolding upon which the universe is built. It reminds us that there is always a scale beyond our reach, always a mystery deeper than we can know, and that science, for all its brilliance, still plays at the edge of a vast and silent unknown. So the next time you walk through space or count time or wonder how small something can be, remember the Planck length. Remember that below a certain point, the questions themselves begin to dissolve. That beyond the smallest length, there may be no length at all. Only probability, only possibility, only the flicker of existence, dancing on the edge of the unknowable. And yet, from that dance arises everything: galaxies, stars, life, consciousness, you, all born from a reality that, at its core, refuses to be seen, but invites us to wonder. The pale blue dot perspective. In 1990, as the Voyager 1 spacecraft prepared to leave the solar system, it turned around at the request of astronomer Carl Sagan and took a final photograph of Earth from a distance of over 3.7 billion miles. The result was a faint image, dark, vast, and nearly empty. And there, barely visible, suspended in a beam of scattered sunlight, was a tiny dot, less than a pixel in size. A pale blue speck floating in a sea of black. That speck was Earth. That pixel contained everything: every city, every ocean, every war and peace, every artist and child, every joy and heartbreak ever known. That image became more than a photo, it became a mirror, a quiet but devastating reflection of our place in the universe. This is the pale blue dot perspective, a cosmic viewpoint that shifts everything we think we know about meaning, significance, and the human condition. The photograph is almost unremarkable at first glance. It lacks color, detail, drama, but that is precisely its power. In that unassuming frame, the entire story of humanity is reduced to a speck. No borders are visible, no flags wave, no empires stand out. From that distance, Earth is not a battlefield or a monument. It is a fragile bead of light, barely distinguishable from the dust and glare around it. And yet, that single pixel holds every triumph and tragedy ever played out. Every language, every idea, every life that has ever drawn breath occurred on that tiny spot. It is the only home we have ever known. Carl Sagan, in his reflection on the image, wrote words that have echoed ever since. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. These words do not just speak to science, they speak to conscience. They remind us of our fragility, not just as individuals, but as a species. We are so small, and yet we behave as if we are the masters of the universe. We fight over lines drawn on maps. We divide ourselves by race, class, and belief. We consume the planet as if it were infinite, forgetting that it hangs in the void without backup, without refuge, without replacement. The pale blue dot perspective humbles us. It dissolves the illusions of grandeur we wrap around ourselves. From a cosmic vantage, the idea of dominance becomes absurd. The Earth could vanish in a blink, and the universe would not notice. The stars would not dim, the galaxies would not tremble. Our solar system is tucked in an unremarkable corner of the Milky Way, which is itself one galaxy among hundreds of billions. We orbit an average star, on a planet neither particularly large nor particularly small. We are cosmically ordinary. And yet, we imagine ourselves central. We imagine our concerns are universal. The pale blue dot reminds us otherwise. But humility does not mean insignificance. In fact, from this perspective, the very existence of life, conscious, questioning, loving life, is all the more remarkable. On that dot, something happened. Atoms formed molecules, molecules formed cells. Cells began to think, to feel, to dream. Consciousness emerged on that pixel. It learned to wonder, to create art, to build cities, to send probes into the darkness. From that tiny world, life reached out, not with violence, but with curiosity. It built machines to see itself from the outside. It took a photograph not of conquest, but of context. That act alone is staggering. In a universe so vast, to be aware of your own smallness is a kind of greatness. The pale blue dot perspective also brings clarity to what matters. It reveals how arbitrary our conflicts truly are, how pointless our pride. The divisions we cling to, religion, nationality, ideology, are invisible from space. They do not exist in the larger view. What we call us and them dissolve into the single fact of life on Earth. From a billion miles away, we are one species, on one planet, under one fragile sky. The perspective is not political, it is existential. It reminds us that we are not alone in the universe, but we are alone with each other. If we ruin this world, we do not get another. If we destroy ourselves, no cosmic cavalry will come. There is also a deeper spiritual thread in this viewpoint, not one tied to dogma, but to awe. To look at the pale blue dot is to see the sacredness of existence, not in temples or texts, but in the silent miracle of being. It is to realize that we are made of stardust, yes, but also that we are stardust that knows it is stardust. We are not spectators in the cosmos, we are part of it. We are the universe reflecting on itself, momentarily aware of its own being. That awareness, however brief, is precious beyond measure. And it exists only here, on this pale blue speck. This perspective also sharpens our sense of time. Earth is 4.5 billion years old. Human civilization occupies only the last blink. All of recorded history, all the gods, kings, wars, inventions, poems, fits into a sliver of planetary time. And that sliver fits into a sliver of cosmic time. The universe is ancient beyond comprehension, and yet here we are, standing on a world warmed by a middle-aged star. Speaking words, asking questions, writing story. We do not know if others exist, we do not know if we are alone, but we do know that, for now, life has emerged here, and that makes this place, the pale blue dot, not just a location, but a responsibility. It is easy in our daily lives to forget this, to become consumed by deadlines, politics, distractions, but the pale blue dot perspective asks us to zoom out, to see not just the street, but the sphere, not just the moment, but the arc of time. It invites us to act with greater kindness, with greater care, not because we are watched or judged, but because we share a common fate. We breathe the same air. We live under the same sun. We depend on the same oceans, forests, and atmosphere. Our fates are entangled. We rise and fall together. This awareness does not erase our differences, but it reorders them. It says, before you are a citizen, you are a human. Before you are a believer, you are a being. Before you are anything else, you are alive on a planet suspended in space. That perspective changes how we treat the Earth. It becomes not just a resource, but a sanctuary. Not just a setting, but a miracle. Every tree, every river, every animal becomes part of something infinitely rare. A world that can think, a planet that can dream. And in that dream, we glimpse the next step. The pale blue dot is not only a mirror, it is a compass. It points us toward unity, stewardship, exploration. It says, yes, we are small, but our dreams are not. Yes, we are fragile, but our minds are vast. We are capable of destroying our world, but we are also capable of healing it, of protecting it, of reaching out to the stars not with conquest, but with care. Not to escape Earth, but to honor it by learning how to thrive beyond it. The photo of Earth from Voyager 1 is more than a snapshot. It is a testament to perspective. It is the universe saying, look at yourself, see what you are, understand your place, and in that understanding grow wiser, grow gentler, grow up. So the next time you feel overwhelmed by the weight of the world, remember the pale blue dot. Remember that everything you love, everything you fear, everything you are exists in a single pixel of light, and that pixel is beautiful. Not because it is big, but because it is home. The cosmic calendar. Imagine shrinking the entire history of the universe, every moment from the birth of space and time to this very instant, into a single calendar year, from the Big Bang on January 1st to now, on December 31st at midnight. This is the cosmic calendar, a powerful metaphor created by Carl Sagan to help us grasp the unimaginable scale of cosmic time. In this calendar, each day represents about 37.8 million years. Each hour spans 1.6 million years. Each second holds more than 500 years of real time. And when you see history laid out like this, a stunning realization emerges. Everything we think of as history, every civilization, invention, belief system, war, and discovery happened in the last second of the last day. Human history is not the center of time, it is the blink of an eye in a much larger story. The universe began 13.8 billion years ago with the Big Bang. On the cosmic calendar, this cataclysmic birth occurs at midnight on January 1st. From nothing came energy. From energy came matter, and from matter came stars. For the first few months of this cosmic year, the universe is hot, dense, and chaotic. Galaxies begin to form by late January. Our own Milky Way emerges in early May. For months, stars live and die, seeding the cosmos with the elements that will one day form planets, oceans, and life. It isn't until September 2nd that our solar system forms. The sun ignites, and the planets take shape from the swirling debris. Earth itself coalesces around September 6th, and not long after, around September 21st, life begins. Not advanced, multicellular life, but simple, single-celled organisms. They rule the planet for billions of years. The first animals do not appear until December 17th, and dinosaurs roam, by December 24th. And only on December 30th do mammals begin to flourish. Human beings, our species, with language, memory, and dreams, do not appear until the evening of December 31st. All of recorded human history fits into the final second of the cosmic calendar. Not the final day or hour or minute, but the last second. The pyramids were built a fraction of a second ago. The Roman Empire flickered just milliseconds past. The invention of writing, the rise of agriculture, the discovery of electricity, the world wars, all of it, compressed into that vanishing instant before the calendar reset. It is breathtaking, it is humbling, it forces us to see our place in a broader context. We are not the protagonists of the universe. We are latecomers to a party that has been going on for almost an entire year. For 364 days and 23 hours, the universe evolved without us. And yet here we are, conscious, curious, capable of constructing this very calendar. That in itself is a marvel. We are the result of ancient processes, of time stretching back beyond memory. Our atoms were forged in stars that died before Earth was born. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were created long before our ancestors walked the earth. The cosmic calendar does not diminish us, it defines us. It reveals that we are part of something vast, that our lives, while brief, are rooted in a history that spans the entire age of the cosmos. It challenges the illusion that the world began when we did. It reminds us that we are not separate from nature, but expressions of it. Brief, luminous sparks in a long and intricate unfolding. We are the universe made aware, reflecting on its own age, its own origins, its own meaning. But this perspective also casts a light on our fragility. If human history is a second long, then our future depends on what we do with that second. We have built great things in an instant, cities, science, culture, but we have also endangered ourselves. Through war, through pollution, through short-sightedness. The cosmic calendar makes clear that Earth has survived far worse than us. But it also makes clear how much we have to lose. We live on a world that has taken 9 cosmic months to prepare for us. And if we are not careful, we could squander it before the year is done. The metaphor is more than visual, it is emotional. It speaks to the heart as much as the mind. When you see human history placed alongside the age of the cosmos, you begin to see what matters, not just your own story, but the story of everything. You see that the stars are not just distant lights, they are ancestral. You see that the oceans, the forests, the sky, They are not mere settings but ancient companions on the path of life. And you see that wisdom comes not from how long something has lasted, but from how deeply it is understood. The cosmic calendar also reframes time itself. We often measure it in hours and days, in schedules and deadlines. But cosmic time has a different rhythm. It does not rush. It does not pause. It unfolds slowly, majestically, patiently. Stars live for billions of years. Galaxies evolve over eons. The movements that shape mountains or form species happen on scales we cannot feel. And yet, we live in the blink. We rise and fall in the moment. Our challenge is to find meaning in that moment, to live fully within the second we are given. And perhaps, in this short second, we can do something extraordinary. Perhaps we can build a world that honors its ancestors, the stars, the earth, the generations past. Perhaps we can build a future that echoes beyond our own time, a future that expands our second into a story that continues, that evolves, that matters. The cosmic calendar is not just a metaphor, it is an invitation. To live with perspective, to act with humility, to wonder, to care, and to remember that time is not what we own, but what we are part of. So the next time you think about history, remember the calendar. Remember that your life is a thread in a vast cosmic tapestry, that the moment you are living in right now rests on the edge of a year-long unfolding that includes the birth of stars, the forming of worlds, the rise of life, and the awakening of awareness. You are living at the very end of December 31st. You are history, compressed into a breath. And that breath is beautiful. Because in that breath you can speak, you can love, you can see the stars and know what they are. You can look back through time not with regret, but with gratitude. And you can look forward not with fear, but with hope. Hope that in the next cosmic second humanity will become not just a flicker, but a flame. A light that endures, a voice that continues the cosmic conversation long into the next year. Quantum vacuum fluctuation. Imagine emptiness. Not a room without furniture, not space without stars, but absolute nothingness. No particles, no light, no matter, no time. Just a perfect void. Now imagine that even in this most stripped-down form of existence, things still happen. Particles emerge uninvited from the emptiness. They appear for a brief moment and then vanish, leaving behind no trace, except perhaps for a ripple, a flicker, a subtle disturbance in the fabric of reality. This is not science fiction. This is quantum physics. At the heart of it lies one of the strangest and most profound ideas in all of science: quantum vacuum fluctuations. The realization that even nothing is something. That emptiness, when viewed through the lens of quantum mechanics, is not a blank slate, but a restless sea of potentiality. In classical physics, a vacuum is truly empty. It is a region devoid of matter, force, or motion. But quantum theory tells a different story. In the quantum world, even the vacuum, the lowest possible energy state, is not silent. It buzzes with activity. At the tiniest scales, governed by the uncertainty principle, energy and particles flicker in and out of existence. This is not metaphor, it is measurable. The vacuum, once thought to be the quiet background against which the play of particles unfolds, is now seen as the main character, endlessly churning with unseen drama. The Heisenberg uncertainty principle is key to understanding this. It tells us that certain pairs of physical quantities, like energy and time, or position and momentum, cannot both be known precisely at the same moment. The more precisely you know one, the less precisely you can know the other. This means that even in a vacuum, where energy is supposed to be at a minimum, there must be fluctuations. Energy can briefly spike, as long as it returns to its baseline quickly enough. These momentary fluctuations give rise to virtual particles. Pairs of particles and antiparticles that pop into being, exist for a fleeting moment, and then annihilate each other. They are called virtual not because they are imaginary, but because they cannot be directly observed. They are mathematical ghosts with real effects. One of the most famous demonstrations of vacuum fluctuations is the Casimir effect. Place two uncharged metal plates very close together in a vacuum, and they will experience a subtle force pulling them together. This is not due to gravity, magnetism, or air pressure, it is due to the quantum vacuum. Between the plates, only certain wavelengths of virtual particles can exist. Outside the plates, all wavelengths are allowed. This imbalance creates a pressure that pushes the plates inward. It is a physical effect caused by empty space, by nothingness itself, exerting a force. Vacuum fluctuations also play a role in the Hawking radiation emitted by black holes. According to Stephen Hawking's theory, when virtual particle pairs form near the event horizon, one particle can fall into the black hole while the other escapes. The escaping particle becomes real, taking energy from the black hole and slowly causing it to evaporate. Thus, even black holes, the most gravitationally intense regions in the universe, are not immune to the frothing chaos of the vacuum. But perhaps the most unsettling implication of vacuum fluctuations is what they suggest about the stability of reality itself. If particles can appear from nothing, what else can? Could entire universes emerge from vacuum fluctuations? Could our universe be the result of such a fluctuation, a quantum bubble that inflated into all of space and time? Some cosmologists believe so. In this view, the Big Bang was not a singular beginning, but the local flowering of a much larger quantum field. Our cosmos could be just one bubble in a vast, ever-foaming multiverse, each universe emerging spontaneously from the vacuum, like froth on the sea. And there is another possibility, darker and stranger. If the vacuum is not truly stable, but only metastable, balanced on a knife edge, it could decay. A lower energy vacuum state could suddenly emerge, expanding at the speed of light, rewriting the laws of physics as it goes. Everything we know, atoms, molecules, chemistry, life, would be erased in a wave of unmaking. There would be no warning, no defense, just the cold realization that the vacuum we live in was never meant to last. This is known as vacuum decay, and while it remains speculative, it is a real mathematical possibility within certain models of particle physics. And yet we live, we think, we feel. Despite the instability beneath us, the world holds together. The vacuum for now behaves itself. But the knowledge that it need not, that beneath every stable form is a foundation of uncertainty, gives us a new perspective. It tells us that reality is not solid, but fluctuating, that permanence is a myth, that the ground beneath our feet is not absolute, but conditional. The universe is not a machine, ticking with certainty. It is a quantum field, breathing in and out with possibility. This understanding also redefines the idea of creation. In many traditions, something cannot come from nothing. But in quantum mechanics, that rule is relaxed. Nothingness is not sterile. It is pregnant with becoming. The void is not a void. It is a field of infinite potential where everything that is or ever could be exists in a kind of waiting. And when the right conditions arise, reality crystallizes out of this chaos, not as a miracle, but as a quantum inevitability. We often think of the world as composed of things, objects, particles, but quantum theory suggests that process, not substance, is fundamental. Particles are excitations in fields. Events arise from fluctuations. The universe is not a collection of stuff, but a dance of energies, woven from the vacuum's own restlessness. Even the space between stars, between atoms, between thoughts, is alive with possibility. The silence is not empty, it is full of whispers. And perhaps that is the deepest message of quantum vacuum fluctuations, that what we see is not all there is, that beneath the visible, the stable, the measurable, lies a realm of wildness, a churning ocean of maybe, and from that ocean rises everything: light, matter, memory, meaning. We are made not just of atoms, but of fluctuations. We are not separate from the void. We are its expression, its shape, its moment of awareness. So, the next time you sit in silence, or look into the dark sky, or wonder what lies beneath the surface of things, remember the vacuum. Remember that even in the quietest space, something stirs. That nothing is truly nothing. That reality at its core is a question waiting to be asked. And in the asking, it becomes time dilation, relativity. Time, for most of us, feels like a constant. It ticks evenly, flows forward, and carries us from moment to moment with a steady, invisible rhythm. Seconds pass into minutes, minutes into hours, days into years. We assume this passage is universal, that no matter where you are or how fast you're moving, time must behave the same way. But Einstein shattered that illusion. According to his theory of relativity, time is not absolute. It bends, it warps, it stretches and contracts. And the faster you move, the slower time flows. For you. This is time dilation, one of the most beautiful and unsettling consequences of special relativity. It suggests that time is not fixed, but personal. That each of us carries our own clock through the universe, and that with enough speed or enough gravity, those clocks can tick at wildly different rates. Imagine two twins. One stays on Earth. The other boards a spaceship capable of traveling near the speed of light. She accelerates to 99.9% of light speed and travels to a star and back. For her, the journey feels brief, maybe a few years, but when she returns, she finds that decades have passed on Earth. Her twin has aged. The world has changed. She is young. Her sister is old. This is not fiction. It is the direct result of Einstein's equations. At near light speeds, time slows down relative to stationary observers. The faster you go, the more extreme the effect. If you could reach the speed of light, which no object with mass can, you would experience no time at all. The entire life of the universe would pass in an instant. This isn't just a thought experiment. Time dilation has been observed. Atomic clocks flown on high-speed jets tick more slowly than those left on the ground. GPS satellites orbiting Earth have to account for both gravitational time dilation from general relativity and speed-based time dilation from special relativity to function properly. If we ignored these effects, GPS systems would quickly become inaccurate. Time dilation is not a curiosity. It is woven into our technology, our physics, and the structure of reality itself. What makes time dilation so haunting is its intimacy. It's not just about clocks. It's about life. For the person moving quickly, time feels normal. She eats, sleeps, thinks, and ages like anyone else. But when she returns, she finds the world changed. The people she left behind have lived longer. History has moved forward without her. In this way, time dilation is a kind of time travel, not into the past, but into the future. A traveler moving fast enough could leap across centuries in the span of a single lifetime. She could leave behind the present and return to a world unrecognizably new. The equations are elegant. The Lorentz factor, denoted by the Greek letter gamma, tells us how much time slows down based on speed. As velocity increases, gamma increases and time stretches. At everyday speeds, the difference is imperceptible. But as you approach light speed, the factor explodes. A journey to the nearest star at 99.999% of light speed would take just a few years for the traveler, while decades or even centuries might pass on Earth. The universe becomes fluid. Time becomes elastic. General relativity introduces another kind of time dilation, one caused not by speed, but by gravity. The stronger the gravitational field, the slower time flows. Near a black hole, time can slow to a crawl. If you stood safely near the event horizon of a massive black hole, a single hour for you might equal years, even centuries for someone far away. This is not speculation. It's been confirmed through observation and dramatized vividly in films like Interstellar, where a few hours on a distant planet meant decades passed for those waiting in orbit. Together, these two forms of time dilation, velocity-based and gravity-based, reveal a universe where time is relative. where now is not a universal concept, where the passage of time depends on your path through space. This challenges our intuition. It suggests that there is no single cosmic clock, only individual clocks, ticking differently based on motion and gravity. Each of us, in a sense, lives in our own timeline. This has deep philosophical implications. What does it mean if time is not absolute? If your future is someone else's past? If simultaneity is an illusion? Relativity tells us that the order of events can change depending on the observer. Two things that appear to happen at the same moment for one person may occur at different times for another. Cause and effect remain intact, but the idea of a single now evaporates. The universe is not a synchronized machine, it is a mosaic of perspectives. And yet, within our own frame of reference, time feels steady. This is the beauty of relativity. It allows each observer to experience time as normal, even while their experience diverges from others. It does not break physics, it expands it. It says, yes, your time is real, but so is everyone else's, and those times are not the same. Reality is not a rigid block. It is a fabric that bends, stretches, and flows with motion and math. This flexibility of time invites us to reimagine what's possible. Could we one day use time dilation for deep space travel? Could we send explorers to distant stars, knowing they will return far in the future, having aged only a few years? It may be the only practical way to reach other worlds without relying on suspended animation or generational ships. If we harness near-light speed travel, we could vault into the future, skipping centuries, seeing what becomes of Earth, becoming time travelers by sheer motion. But the emotional weight of time dilation is also profound. Imagine saying goodbye to someone, knowing you will return to find their grandchildren. Imagine watching a message from Earth, knowing decades have passed since it was sent. Time dilation creates a strange loneliness, a gap between lives. It stretches the thread of connection across years and light years, and yet in that gap, there is awe, the kind of awe that comes from understanding that time is not a prison, but a path. That our moment is not the only one. Time dilation also reminds us that perception is not always truth. We live in a tiny slice of the universe, moving at ordinary speeds under moderate gravity. We assume this is normal, but relativity shows us that normal is local. The universe allows for extremes we rarely encounter, and in those extremes, reality reveals its deeper nature. Time, space, mass, all bend with motion. The rules shift, the world flexes. And we, once so certain of time's grip, find ourselves floating in something far more fluid. This insight does not diminish our lives, it enriches them. It tells us that the seconds we feel, the hours we measure, are not universal, but they are meaningful. They are part of our journey through space-time, and they are shared in some mysterious way with every clock in the cosmos. Every star, every planet, every traveler moving through the darkness carries their own time. Together, we make up the tapestry of existence. So the next time you feel time slipping through your fingers, remember, time is not a thing that flows past you. It is something you move through. It stretches and bends with your motion. It pulses differently near mountains, near stars, near speed. And every moment you live is part of a dance far larger than yourself. You are not just a prisoner of time, you are a participant in its unfolding. In the end, time dilation is not just a scientific fact, it is a philosophical invitation to rethink what it means to age, to wonder what it means to share time with someone, to feel the weight of a second, knowing it is not the same everywhere, and to marvel at a universe that, in bending time, reveals how precious each moment truly is. The great filter. We look into the night sky and see a sea of stars, thousands with the naked eye, billions through telescopes. Around those stars spin planets, trillions by some estimates, many of them in the habitable zone, where conditions might be just right for life. The ingredients for biology appear common: Carbon, water, sunlight, chemistry, they are not rare gifts, they are scattered across the galaxy. And yet we see no signs of life. No signals, no structures, no civilizations spanning the stars. This silence, this emptiness, is deafening. It begs a question: where is everybody? This is the heart of the Fermi Paradox, and within it lies a darker, more disturbing idea: the Great Filter. The Great Filter is the notion that somewhere along the path from dust to thinking, technological beings, there is an obstacle, a barrier so difficult to cross that almost no species make it through. It is a kind of cosmic kill switch, unseen, silent, but nearly universal. Its presence would explain the silence. It would answer why, despite the age of the universe and the abundance of planets, we see no signs of intelligent life beyond Earth. It would mean that life either fails to emerge at all, fails to advance, or destroys itself before reaching the stars. To grasp the concept, imagine a timeline. On the left is lifeless matter. On the right is a galaxy filled with civilizations capable of communication, exploration, perhaps colonization. Between those 2 points lies a series of steps: the formation of life, the evolution of complex cells, the development of intelligence, the rise of technology, and the survival of that technology long enough to expand beyond a single planet. The Great Filter is one of those steps, perhaps more than one, and most species, maybe all, fail to get past it. There are 2 terrifying possibilities embedded in this idea. The first is that the filter lies behind us, that the difficult step has already occurred. Maybe life itself is astonishingly rare. Maybe Earth is one of the only places where chemistry stumbled into biology. Or maybe life arises often, but complex, multicellular organisms are almost impossible. Perhaps the leap from simple cells to intelligent brains is so rare that we are among the first, if not the only, to make it. If so, we are incredibly lucky. We have already passed through the narrow gate. The silence in the universe would not be a warning, but an eerie confirmation that we are rare, fragile, and precious. But the second possibility is worse. It is that the filter lies ahead of us, that we are not special for having made it this far, but typical in our trajectory, and that soon, like all the others, we will fall. This version of the Great Filter is the one that keeps philosophers and scientists awake at night. It suggests that the step from technological civilization to spacefaring species is the most perilous of all, that somewhere between the invention of radio and the colonization of nearby stars lies a self-destructive wall, one we have not yet hit, but might be approaching. This filter could take many forms. It might be ecological collapse, civilizations consuming their resources faster than they can replenish them. It might be war, nuclear or otherwise. It could be artificial intelligence, machines surpassing their creators and choosing paths indifferent or hostile to life. It might be biotechnology, engineered pandemics spreading faster than they can be contained. Or it could be something we haven't imagined. A trap inherent to intelligence, a flaw in cognition or culture that inevitably leads to ruin. The filter doesn't have to be dramatic. It might be subtle. A slow, quiet failure to sustain complexity, a gradual decline in innovation, a steady erosion of cooperation. Civilizations might simply lose the will or the means to explore. They may retreat inward, collapse, or stagnate. The result is the same: silence, darkness, the absence of any sign that someone else made it. And yet here we are, aware, questioning, listening. That fact alone is extraordinary. It means we've already passed through some filters. Life began, it persisted, it became conscious, it built tools, language, science. Those are not trivial achievements. They are rare, maybe vanishingly so. But we don't know how far along the path we really are. We don't know if the worst is behind us or ahead. That uncertainty is the shadow of the Great Filter. Some hope that the silence in the cosmos means the filter is behind us, that life is so rare we might be alone, not because others failed, but because they never started. In that case, Our duty is clear. We must protect this rare flicker of consciousness. We must survive, grow, and spread, to preserve life where none may otherwise exist. But others fear the silence means the filter is yet to come, that the quiet sky is not peaceful, but ominous, that civilizations like ours light up briefly and then vanish. And yet hope persists. We are not doomed. Awareness brings agency. The great filter is not a prophecy, it is a possibility, and possibilities can be altered. If the danger lies ahead, then perhaps we can identify it, prepare for it, and pass through. Perhaps what makes us rare is not that we are intelligent, but that we are wise, that we can foresee what others could not, that we can avoid the cliffs that others blindly walked over. The great filter also reframes how we view our present moment. We are living in a fragile window, the early technological era. We have the power to destroy ourselves, but not yet the ability to protect ourselves from every threat. We walk a tightrope between progress and peril. The choices we make now may determine whether we become one of the few who pass through the filter, or one more voice lost to silence. This awareness can be paralyzing, but it can also be galvanizing. It means that what we do matters, that peace, sustainability, cooperation, and foresight are not luxuries, they are necessities. Our future is not guaranteed, but it is possible, and that possibility gives meaning to every action we take. The filter also challenges our assumptions about intelligence. We often imagine that once a species becomes smart, progress is inevitable. But the filter reminds us that intelligence is not enough. Evolution did not prepare us for the long term. It prepared us to survive the short term, to avoid predators, find food, reproduce. Our minds are shaped for now, not forever. To survive the filter, we must transcend that limitation. We must think not in years, but in millennia. Not in profits, but in consequences. Not in borders, but in biospheres. The great filter is not just a theory, it is a mirror. It shows us what we might become and what we might not. It asks us who we are, what we value, and how far we are willing to go to protect the fragile miracle of consciousness. It reminds us that life is not inevitable, that complexity is hard-won, that survival is a choice, not a guarantee. So when you look into the stars and hear nothing, don't despair. Listen more closely. The silence is not just absence. It is a question, and how we answer it will define our future. Multiverse Theory. Imagine drifting across a vast ocean with no land in sight. Waves stretch in all directions, and the sky above reflects your loneliness. But then you begin to wonder, what if beyond the horizon, hidden by distance or time, there are other islands? Other worlds like yours, floating silently, untouched and unreachable. Now replace the sea with space-time. Replace the islands with universes. This is the heart of the island universe theory. The idea that our universe is not all there is, but one cosmic bubble among countless others, scattered across an infinite multiversal ocean, each of them sealed off, isolated, forever out of reach. Each of them complete in itself. Ours is just one island, a beautiful one, yes, but not the only one. This idea emerges not from fantasy, but from the mathematics of cosmology, particularly a concept known as cosmic inflation. In the earliest fractions of a second after the Big Bang, our universe is thought to have undergone a rapid and exponential expansion. This inflation smoothed out the cosmos, making it uniform and flat, but some theories suggest inflation never really ended. Instead, it continues in other regions of space. In some areas, pockets of space stop inflating and form universes like ours. In other areas, inflation continues. The result is a kind of eternal bubbling, a universe giving birth to other universes, endlessly. Each bubble becomes an island. Each island floats in a sea of inflating space. Each is cut off from the rest. These universes may have different physical laws, different constants, different particles. Some might be sterile, filled with nothing but cold radiation. Others might be violent, where gravity is too strong or atoms can't form. But some, perhaps, are like ours, with stars, with chemistry, with life. They are not parallel worlds where another version of you exists. They are truly separate realities, with their own histories, their own timelines, their own physics. They are disconnected by nature, not just by distance. The term island universe was once used to describe galaxies before we understood their true nature. Astronomers once debated whether the spiral smudges in the night sky were part of the Milky Way or separate island systems. We now know that each galaxy is a vast collection of stars, bound by gravity, drifting in a cosmic sea. The island universe theory is a similar shift, but on a deeper level. It suggests that our entire observable universe, everything we've ever seen, measured, or imagined, might be just one region in a vastly larger and more fragmented reality. But if these other universes exist, why can't we see them? Why can't we travel there? The answer lies in the nature of space itself. Each bubble universe is expanding, and the space between them is inflating faster than light can travel. Even if two universes were born side by side, the space between them would grow too rapidly for anything, information, matter, even light, to cross. They are not just far away, they are causally disconnected, sealed off by the very fabric of reality. To us, they are beyond the horizon, not just out of reach, but fundamentally unknowable. This might seem discouraging, but it also opens a window to wonder. The island universe theory suggests that reality is bigger than our imagination, that what we call the universe is just a patch, a fragment, a single note in a much larger symphony. It challenges the idea that our world is special. It dethrones the notion of a singular cosmos and replaces it with a cosmic archipelago, a vast chain of isolated domains, each with its own story. And in doing so, it reframes our place in existence. If we are not the only universe, then our values, our struggles, our victories, while meaningful, are not universal. They are local. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of the universe. And now, perhaps, the universe is not the totality of being. We are always discovering that the center is somewhere else. Yet this does not diminish us. It humbles us. And in that humility lies a deeper kind of meaning. If reality is made of countless islands, and we are aware of ours, then perhaps our purpose is not to conquer the cosmos, but to understand it. To explore not just with rockets, but with reason. To reach not with ships, but with thought. The island universe theory reminds us that even in isolation, we are connected by curiosity, by mathematics, by the silent unity of existence. Some physicists hope that we might one day detect evidence of other universes, that collisions between bubbles might leave imprints in the cosmic microwave background, that particles might deviate from known behavior in ways that point to extra-dimensional influence. But these hopes are fragile. The nature of other universes may be such that no experiment can ever reach them. We may live in a cosmos where most of what exists is forever hidden. And yet, that doesn't make the theory less powerful. The island universe theory is a tool of imagination, a scaffolding for understanding how vast and varied reality might be. It forces us to ask, what is real? What can be known? Are we limited by our instruments or by the structure of space itself? And what does it mean to be part of a universe that may be just one bubble among countless others? It also sharpens the Fermi Paradox. If intelligent life exists in other universes, we will never hear from them. The silence between stars is explainable, but the silence between universes is permanent. No signal, no probe, no journey can breach that barrier. Each island must live, and perhaps die, alone. This is a lonely idea, but it is also profound. It tells us that life, if it arises at all, must find its meaning within itself, not from the cosmos at large, but from its own island shores. And yet there is beauty in this vision. The idea that there may be other worlds forever out of reach gives the universe depth. It makes our own world more precious, not less. We are a self-aware expression of one pocket of reality, watching the waves of the greater sea, imagining what might lie beyond. And that imagination is a kind of travel, a kind of contact. We may never visit other universes, but we can conceive them, and in doing so, we expand the edges of our own. So what should we do with this knowledge or this possibility? Perhaps we should treat our universe as a gift, a place not of scarcity, but of wonder. Perhaps we should explore its mysteries, cherish its life, and protect its beauty, not because there are others, but because this one is ours. The island universe theory teaches us that what we have is rare, not because nothing else exists, but because nothing else may ever touch us. We are an island, but we are not adrift. We are home. And perhaps, in some distant universe, on some other island, a different being wonders the same thing, wonders if there are others, wonders if their bubble is alone, and maybe they too look at their stars and dream of crossing an ocean that can never be crossed. That is enough. That dreaming connects us. So the next time you look into the night sky, remember, beyond the stars you see, beyond the galaxies and voids, beyond even the edge of time as we know it, there may be more. Not in the way we once imagined, not planets or moons, but entire universes, entire sets of laws, entire poems of physics written in alphabets we will never read, and we, here, now, are a verse in one of them. A quiet island lit from within,